Abell 2261 is one of the strangest galaxies ever found. It is hidden in the constellation Hercules, about 2.7 billion light-years away, and its center black hole has just disappeared. Telescopes from Hubble to Chandra have looked into the galaxy's center and found nothing. Every galaxy this big should have a giant black hole at its core. There are no X-rays, a bright center, or any sign of the engine that should hold a galaxy this big together. It's been a puzzle for scientists for more than 10 years. How can a galaxy lose the thing that makes it what it is? We're going to explore Abell 2261 today, which is the case of the lost supermassive black hole. The galaxy with no heart. The name Abell 2261 doesn't sound like much until you learn that it stands for a crime scene in the galaxy, this cluster in the constellation. Hercules is about 2.7 billion light-years away. It is home to a brightest cluster galaxy, BCG, that should be ruled by a huge supermassive black hole according to all the rules of how galaxies form and grow. Its center, instead, looks empty. Do not faint. Not quiet. Not full. When the Hubble Space Telescope first imaged the central galaxy, catalogued as a 2261 BCG, it showed something nobody expected: an immense flat core more than 10,000 light-years across. By comparison, the Milky Way's central bulge barely spans 1/5 of that. In most galaxies, brightness rises steeply toward the center, where stars crowd around a dense gravitational well. But here, the light profile simply levels off, as if the heart of the galaxy had been scooped out. That discovery alone was headline-worthy in 2012, when a NASA-backed team published it in the Astrophysical Journal. The galaxy's missing peak implied that stars in its center had been physically flung outward, a process thought to occur when two supermassive black holes merge and violently kick surrounding stars aside. The problem: once the merger ends, the resulting black hole should settle back into the middle and keep feeding on gas, blazing in X-rays or radio. Yet no source of radiation exists there. Even after zooming in and running models, they still couldn't find it. Most of the time, the most massive galaxies in the universe have equally massive engines at their centers. Some of these engines are over 10 billion times the mass of the Sun. The brightness and speed spread of Abell 2261 make it look like it should be in that top class. Instead, the core is eerily calm. There is no radio spot, no X-ray point, and no center that can be found. The suspicion formed quickly. Maybe the black hole didn't just stop feeding. Maybe it's gone. In the years since, a 2261 BCG has become a textbook case for every scenario astrophysicists debate when black holes go missing. It helps to picture the size to understand how strange that is. It's almost 1 million light-years across, which is bigger than our whole local group. Around that open, underdense body in the middle is a group of older, reddish stars. Hubble saw a few small bright spots spread out across this hill. These are star clusters that don't look like they belong there, like crumbs left over after a crash. In theory, one of them could hide a black hole that has gotten out of control by surrounding it with its own small group of stars. If so, the story turns cinematic. Two massive galaxies collided, their central black holes spiraled together and merged. Gravitational waves blasted outward, and the recoil shoved the new black hole thousands of light-years off-center, dragging a pocket of stars with it. The leftover galaxy would appear just like Abell 2261 does now: flat-cored, slightly lopsided, and missing its gravitational monarch. That's the gravitational wave recoil hypothesis, and it's among the most thrilling possibilities in extragalactic astronomy. Detecting even one such kicked-out black hole would confirm a key prediction of Einstein's general relativity on the largest scales. But excitement aside, the data remain frustratingly inconclusive. When the Chandra X-ray Observatory targeted Abell 2261, astronomers expected to see at least a faint central glow from hot gas falling into a quiescent black hole. Nothing. They extended the exposure, 100 kiloseconds of new data added to 35 kiloseconds of archival observations, and still came up empty. Even the 4 off-center knots, each a prime suspect, were silent in X-rays. If a supermassive black hole lurks in any of them, it's accreting material at less than 100,000th the rate of the Milky Way's own central black hole, Sagittarius A star. That's invisible level quiet. Radio telescopes helped solve the puzzle even more. The Very Large Array picked up faint scattered radio emission coming from a little ways away from the galaxy's center. This could be a holdover from when the galaxy was busy millions of years ago. The jets look old because their lobes are loosened up and going away. Whatever gave them power hasn't worked in a long time. The black hole has moved if that radio source shows where it used to be. Chandra mapping shows the densest region of intracluster plasma displaced from the stellar core, suggesting the entire central potential well might have shifted. That displacement could come from a massive recoil, or from simple sloshing caused by past mergers. Either way, it means this galaxy's inner structure is still settling after something catastrophic. Simulations back the idea that when 2 supermassive black holes carve through a stellar core, they fling stars outward, creating precisely the kind of huge, flat light profile Hubble measured. The bigger the binary, the larger the evacuated region. For Abell 2261's core to be this enormous, the central black hole, or black holes, must have been exceptional, likely in the tens of billions solar mass range. Yet even with that expected heft, it's invisible. Could it be hiding because it doesn't have any gas and can't be seen? This is what the dormant monster theory says. The black hole could still be there, sitting quietly in the middle after using up all the fuel it could find. But dynamical models of the motions of the stars suggest that the center might not even need a huge dark object to explain the speeds we see now. This is another argument against the idea that the universe is hidden, but present. The biggest galaxy core ever seen. Not only does Abell 2261 have a normal galactic center, it also has the biggest and flattest core ever seen. Astronomers thought the maps made by Hubble's advanced camera for surveys were wrong at first. The galaxy's brightness didn't rise steeply toward the middle like scientists thought it would. Instead, it stayed the same across an area more than 10,000 light-years wide, which is so big it could fit the Milky Way's bulge and still have room to spare. That's like finding a building without its top floors in terms of cosmic design. In most massive galaxies, gravity and stellar density produce a smooth inward climb in brightness, peaking where the supermassive black hole sits. But Abell 2261 breaks that pattern. The core is too flat, too broad, and crucially, too empty. It's not an observational glitch. Multiple telescopes confirmed it. Such an enormous light deficit means millions of stars have been physically displaced. The only known mechanism powerful enough to do that is a binary black hole slingshot effect, where 2 merging black holes eject surrounding stars as they spiral inward. The larger the binary, the more severe the evacuation. For Abell 2261's central void to reach this size, the pair that carved it must have been absolutely titanic. The best fits to the galaxy's structure suggest a core radius exceeding 3 kiloparsecs, at least 3 times larger than any previously measured. Based on established scaling relations, that translates to a black hole mass somewhere around 10 billion solar masses, maybe more. That would make it one of the heaviest ever inferred, comparable to the monster at the center of quasar Ton 618, but in a galaxy far older and quieter. Yet unlike those luminous quasars, there's no sign of accretion here, just starlight and silence. When researchers compared the galaxy's shape with simulations, the conclusion was inescapable. Something catastrophic happened in Abell 2261's past. Either 2 supermassive black holes merged and then recoiled away from the center, or they're still locked together in a stalled binary that never completed the dance. Both scenarios can create vast flat cores. In a completed merger, The newly combined black hole can receive a gravitational recoil kick from uneven gravitational wave emission, sending it careening thousands of light years before friction slows it down. If that's what happened, the black hole and its immediate entourage of stars could now be wandering somewhere near the edge of that gigantic hollow. The optical structure supports that story. Hubble's images show 4 bright knots embedded inside the core, like islands of light adrift in a stellar sea. Each one could be the remnant of a smaller galaxy shredded during the merger, or perhaps the star cluster still bound to a recoiling black hole. To tell the difference, astronomers need velocity data, how fast those stars move relative to the galaxy. If one knot shows abnormally high dispersion, that's the likely hiding spot. What's more peculiar about this case is the difference between the core's optical center and the galaxy's mass center. It's not perfectly lined up, it's moved by almost 0.7 kiloparsecs. The fact that it isn't balanced means that the galaxy's real heart, its center gravitational potential, has changed. It should settle down quickly, but in Abell 2261, the movement seems to have stopped, as if the balance had never been restored. The system should have been back to normal a long time ago if there was still a giant black hole there. The missing black hole idea is strengthened by the fact that it hasn't happened yet. Chandra's deep observations reinforced that conclusion. A galaxy this massive should glow with X-rays near its core, where hot gas condenses and feeds the central engine. Yet the X-ray luminosity is essentially zero at the nucleus. Even if a supermassive black hole were quietly accreting, it should radiate more strongly. The absence of any detectable point source is like scanning for a bonfire in total darkness and finding only cold ash. Meanwhile, radio data from the Very Large Array revealed faint lobes roughly 6.5 kiloparsecs from the galaxy's center, relics of past jets from an active nucleus. The age of those radio lobes is estimated at tens of millions of years, meaning Abell 2261's black hole, if it still exists within the galaxy, has been dormant for an extraordinarily long time. The orientation of those relics doesn't line up perfectly with the stellar core either, again suggesting the central engine might have shifted. All of this makes Abell 2261 a strange cosmic puzzle. With a stellar mass of more than 1 trillion suns, it's one of the brightest galaxies in its cluster. But the expected gravity center isn't there. If it really doesn't have a black hole, that calls into question one of the most important ideas in galaxy formation theory, since the mass of the galaxy bulge has been linked to the mass of black holes almost everywhere. If the black hole has only moved, it is the first real proof that gravity waves can push even 10 billion solar mass monsters into space. In either case, our models need to be changed in some way. Where's the central black hole? Every time scientists look at Abell 2261, they keep coming back to the same hard question. Where is its giant black hole? From everything we know, it must exist. It's impossible for a galaxy this big and bright to form without one. Its stars move around too quickly, there isn't enough light in the center, and it has too much mass for gravity to hold it all together. Astronomers looked for the small, high-energy sign that every other brightest cluster galaxy has, but the spot was empty. The normal beacon, which is the bright light of matter dropping into a gravitational void, wasn't there at all. The first serious search began in 2012, right after Hubble revealed Abell 2261's enormous pancake-flat core. Astronomers immediately called in NASA's Chandra X-ray Observatory, expecting to see the telltale signal of accretion, hot gas heating to millions of degrees as it spirals toward the black hole. But the results were astonishingly quiet. Chandra's detectors recorded nothing above background noise. Even at the sensitivity limits, there was no point source emission at the galaxy's center, no compact knot, no flicker of energy. To put that in perspective, even our Milky Way's dormant black hole, Sagittarius A star, emits weak X-rays from infalling gas. Abell 2261's central region is so cold and silent, it makes Sagittarius A star look busy. If a black hole still resides in the middle, It's consuming almost nothing. Its feeding rate so low that it's effectively invisible. Statistically, that's possible, but extremely unlikely for a galaxy of this size. The next step was to widen the search. Astronomers began scanning the 4 bright stellar clumps inside the core, strange islands of light possibly left behind by galaxy mergers. Each was a potential hiding spot. The thinking went like this. If Abell 2261's black hole was kicked from the center during a massive merger, it might be dragging a few million stars with it. A hypercompact stellar system. One of those clumps could conceal the black hole, its gravity binding the stars tightly around it. But again, nothing. Chandra found no X-rays. The Very Large Array, VLA, found no compact radio source, and spectroscopy showed no obvious velocity spikes indicating a massive object. If the black hole isn't at the center and isn't in one of the knots, could it have escaped the galaxy entirely? That's the boldest and most exciting hypothesis. During the final moments of a black hole merger, gravitational waves can shoot off asymmetrically, giving the merged object a recoil kick at thousands of kilometers per second. In smaller galaxies, that's enough to launch the black hole straight into intergalactic space. Even in a massive giant like Abell 2261, such a kick could carry it tens of thousands of light years from home. This idea is backed up by simulations. When 2 very large black holes join together, they can send out gravity waves like rocket smoke. If one side gives off more energy than the other, the new black hole moves the other way, like a gun recoiling in space. The speed could be faster than 5,000 kilometers per second for a system with 1 billion solar masses. You could leave a galaxy behind that quickly. If this scenario played out in Abell 2261, we're catching it after the chaos, when the core has already relaxed, but the engine is gone. The galaxy would keep glowing for billions of years, its stars orbiting an invisible absence. What's left behind is exactly what we see, a huge round cavity, faintly offset from the galaxy's outer halo and silent across every spectrum. Some researchers argue the black hole might still be there, just stalled. After a major merger, the 2 central black holes spiral together through dynamical friction, kicking out nearby stars and forming a binary system at the heart. But at some point, they can reach a critical distance, just a few light years apart, where they run out of nearby stars to sling away. The merger stalls. Without a fresh source of friction or gas drag, the binary can hang suspended indefinitely. If that's happening in Abell 2261, both black holes could still be in the center, orbiting invisibly, waiting for a trigger, perhaps another infall of gas or a small galaxy, to finish the merger. This stalled binary model fits certain clues. The core's huge, flat structure could have been sculpted by a long-lived binary ejecting stars for hundreds of millions of years. The system's symmetry suggests no violent recoil has distorted it recently. And because no AGN activity is visible, the binary may simply lack fuel. In other words, the black holes didn't run away. They just fell asleep mid-dance. The galaxy's light profile is not perfectly centered. The inner brightness peak is slightly displaced relative to the outer halo, implying motion. If the system were truly stable, that offset shouldn't exist. Some astronomers suspect this asymmetry is a lingering trace of the black hole's recoil, a snapshot of it leaving or perhaps returning to the core after a massive kick. Either way, something enormous has been rearranged. When Chandra's X-ray map is compared to the optical image, the densest gas pocket sits northwest of the stellar center, as though the gravitational potential well itself had shifted. That kind of sloshing could result from the black hole's departure or from the merger that made it. And if Abell 2261 really did lose its supermassive black hole, the next mystery writes itself. Where in the universe do you even begin to look for it? The 4 bright knots. Hubble saw 4 tiny points of light, which are called knots, inside Abell 2261's huge, hollowed-out heart. Astronomers see them as proof from a crime scene, even though they don't look like much. Each knot is a tight group of stars that floats in a place that shouldn't have anything that thick, Each knot is several hundred light-years across. These clumps could be the last friends of a supermassive black hole that has gone missing, or they could just be the leftover pieces of a cosmic crash. When the Hubble team first analyzed them, they were struck by how misplaced the knots appeared. In most galaxies, the light smoothly brightens toward the center, but Abell 2261's profile flattens, and then, out of nowhere, these bright specks interrupt the smoothness. Their symmetry is off, their spacing irregular, and one sits slightly north of the geometric center, where the black hole ought to be. That one quickly became suspect number one. If Abell 2261's black hole was kicked out after a merger, theory predicts it would drag a small envelope of bound stars with it, a hypercompact stellar system only a few hundred light-years wide. The gravitational hold of such a cluster would keep those stars moving at hundreds of kilometers per second, producing a high internal velocity dispersion. So if any of these knots show unusually fast-moving stars, that's where the black hole hides. Spectroscopic follow-ups have tried to measure that, but the results remain blurry. The galaxy's distance, 2.7 billion light-years, pushes even Hubble's resolution to its limits. The knots blur together with surrounding starlight, masking fine details. So far, none display clear velocity spikes, though the data's uncertainty leaves room for small, unseen accelerations. Still, it's clear these knots aren't typical star clusters. They're too large, too luminous, and too ancient. Most likely, they're remnants of satellite galaxies swallowed during Abell 2261's chaotic assembly. The naked cores of smaller galaxies may be what these are. They may have joined with the main body billions of years ago. Then each knot would have had its own black hole at one point. If two of those black holes sank toward the center and joined together, the one that survived might have been thrown out, but the star cores that were left behind would have stayed put. The pattern we see, the knots spread out like pieces over the first 10,000 light-years, almost perfectly fits that situation. But what if the central black hole never left? Then the knots might tell a different story. In that case, they could be dense star clusters orbiting within the still hidden gravitational field of the black hole. Their distribution might trace the edges of the evacuated zone created by the binary that once occupied the core. In that reading, the knots are landmarks, not suspects. The deep X-ray images taken by Chandra tried to break the tie. In X-rays, one knot should give off a weak glow if it had a growing black hole inside it. As a result, again, nothing. All four of them did not light up. This is also true for radio data from the Very Large Array. There is neither a tight jet nor an emission peak. If there is a black hole, it is either completely still or hidden so well that even billion-second exposures can't see it. The knots are notable because of how they line up with the offset core of Abell 2261. The brightest one is near the direction of the galaxy's visual shift, which is a little to the northwest of the gas center of the cluster. There is a reason for that spatial connection. It suggests that the event that moved the galaxy's center also put these knots in place. All it would take is one stroke of physics to explain both patterns. Chandra's deep look. Any telescope, not just Abell 2261 AS, could figure out what happened to the black hole that went missing. It was made to pick up X-rays from the universe's hottest and most energetic spots, and it regularly finds black holes halfway across the universe. Astronomers pointed it at Abell 2261, expecting to find a bright point source in the middle of that huge galaxy, but all they got was quiet. The observations were exhaustive. Over 100,000 seconds of fresh exposure combined with 35,000 seconds of archival data gave Chandra an unprecedented view of the cluster's inner regions. That's long enough to reveal even a faintly feeding black hole, a signal as small as 1/10,000,000th the brightness of a typical active galactic nucleus. Yet, the final image showed no compact X-ray spot in the core. The result was definitive. If a supermassive black hole exists there, it's either completely dormant or gone. This absence of radiation is a problem because even sleeping black holes usually emit something. In galaxies, this massive hot gas from the surrounding intracluster medium should constantly drift inward. As it nears the black hole's gravitational influence, friction heats that gas to tens of millions of degrees, making it glow in X-rays. But the core of Abell 2261 is stone cold. The surrounding hot plasma emits a diffuse glow, yet there's no bright peak at the center, no sign of an accretion flow or compact nucleus. Researchers like Kaihan Gultekin and his team used the data to set upper limits on what the hidden black hole's brightness could be. The numbers were shocking. If one truly lurks inside the galaxy, its luminosity must be less than a trillionth of its Eddington limit, the theoretical maximum for a black hole's radiation before it blows away its own fuel. In other words, the engine would have to be consuming virtually no matter at all. Even Sagittarius A, the Milky Way's faint nucleus, shines thousands of times brighter relative to its mass. Chandra also examined the 4 bright knots that Hubble had revealed inside the core. If the black hole had been kicked away during a merger, it might now sit inside one of those compact clumps, feeding quietly. Astronomers targeted each one separately, but again, there was silence. No X-ray flare, no concentrated heat, just background cosmic noise. That lack of emission has 2 possible interpretations. First, the black hole could be completely quiescent, a dormant monster with no surrounding gas to eat. Second, the black hole might not be there at all, having been recoiled from the galaxy after its last merger. To decide between those options, scientists compared the X-ray results with radio data from the Very Large Array, VLA. The VLA's wideband surveys revealed faint, ghostly radio lobes extending roughly 6.5 kiloparsecs from the center, signatures of a once-active galactic jet. Those lobes indicate that at least tens of millions of years ago, Abell 2261 did host an active nucleus. Since then, the jets have faded into relics. If the black hole still occupied the same spot, you'd expect to see a weak core in both X-rays and radio. Instead, the radio emission is slightly off-center, displaced to the northwest. That spatial offset lines up suspiciously well with the direction of the galaxy's optical asymmetry. It's as if the black hole turned off, drifted away, and left its dying jets behind. Chandra's map of the hot gas halo around the galaxy shows a similar offset. The densest, hottest gas pocket is not centered on the stars, but shifted in the same direction as the radio relic. This kind of misalignment is often caused by a recent gravitational disturbance, a sign that the entire galactic core might have been physically displaced. In normal cluster galaxies, the X-ray and optical peaks line up precisely. In Abell 2261, they don't. Still, astronomers are careful not to overinterpret. The hot gas could have been stirred by a galaxy merger unrelated to the black hole, or by cluster-level sloshing that nudges the plasma around. But even those explanations reinforce the same story. This system experienced a violent past, one powerful enough to unseat its central object. Radio breadcrumbs. Radio waves added whispers to the sound of silence that Chandra picked up. These were small signs that Abell 2261's lost black hole was once very noisy. Astronomers used the Very Large Array, VLA, to make deep studies and found 2 diffuse bands of radio emission rising from the center of the galaxy. Some quasars have bright jets, but these lobes aren't those. Instead, they're ghosts of an engine that stopped working tens of millions of years ago. Still, the way they look and where they are may help us figure out where that engine went. The radio structures stretch roughly 6,500 light-years from the galaxy's center and curve in a way that suggests they once emerged from a supermassive black hole. The problem? The lobes aren't symmetrical. Their apparent midpoint, the spot where the black hole should sit, is offset from the galaxy's optical center. That displacement, confirmed in multiple frequencies, perfectly matches the direction of the galaxy's core asymmetry seen in Hubble and Chandra images. It's as if all the evidence is pointing the same way. Something massive shifted northwest. Radio relics like these act like cosmic footprints. They persist long after an active galactic nucleus shuts down, because the relativistic electrons that power them slowly lose energy but don't vanish instantly. Over tens of millions of years, they expand and fade. The estimated age of Abell 2261's lobes fits this timeline well, suggesting its nucleus was last active roughly 50 to 100 million years ago. That means the galaxy's black hole was once a quasar-class powerhouse, blasting twin jets across intergalactic space before suddenly going dark. What could have silenced such a colossal engine so abruptly? The leading idea is recoil, that gravitational wave kick following a merger. When two massive black holes collide, the merged remnant can rocket away from its birthplace, cutting off the flow of infalling gas that fuels its jets. Without a steady food supply, the jets sputter out, leaving fading lobes like these. The offset direction of the radio relics even hints at the path the black hole might have taken as it drifted outward from the galaxy's center. On the other hand, the radio bands that are dying out could be signs of a more normal shutdown. The black hole might still be there, but it might be out of fuel. Brightest cluster galaxies are found in hot, low-density places where gas is often too thin to accrete properly. When the reserve around the engine runs out, it turns off by itself, leaving behind relic lobes that age slowly in the plasma of the cluster. But if that were true, the lobes should stay in the middle of the visual core. They don't. The runaway theory is still alive because of that continuous offset. The polarization and spectral index of the lobes strengthen the picture. Radio astronomers find that older jets lose their high-energy electrons first, causing their emission to steepen in spectrum over time. Abell 2261's lobes show exactly that steep fall-off, consistent with ancient, not current, activity. There's no compact core or flat spectrum component, a sure sign that whatever powered them has been dormant for ages. It's captivating that the radio map, the X-ray map, and the optical map all have different ideas about where the center of the galaxy is. The stars, the hot gas, and the old radio bands all point to a slightly different middle point, thousands of light years apart. This tension in space says that the system is still settling down after a big shock. Astrophysicists call it cosmic inertia, which means that even hundreds of billions of stars haven't been able to readjust around the missing mass yet, after a gravity push so strong. Flat core, big problem. The center of Abell 2261 is not only big, it's too big to be explained normally. Astronomers measured the inner light profile when Hubble first mapped it, and couldn't believe what they saw. A center area that was so flat and long that it broke all known scaling rules. The center brightness of large galaxies generally gets brighter as you get closer to the nucleus. This is because of the supermassive black hole's pull on the galaxy. That bright peak isn't there in Abell 2261 though. Instead, the starlight drops off quickly, leaving a 10,000 light-year-wide flat area that is very dim. It's the biggest core ever found, and something big should have happened there for it to exist. To understand why, you have to know how galaxy cores form. When two galaxies merge, their black holes sink toward the center through a process called dynamical friction. They drag surrounding stars along and toss others outward. The pair eventually settles into a tight binary, and every time they fling a star away, the core gets larger. Once they finally merge, they carve out a cavity of missing stars. It's like a cosmic snowplow clearing everything around it. The bigger the black holes, the wider the cleared zone. Abell 2261's flat core suggests a binary so massive that it ejected billions of stars before vanishing. The numbers don't add up without something extreme. A galaxy with 1 trillion solar masses of stars should host a black hole weighing roughly 10 billion suns. That's the same mass range inferred from the core's shape. But if such a giant still sat quietly in the middle, gravity would have drawn the surrounding stars back into a steeper distribution long ago. The persistence of that flat region implies the central mass isn't there to restore equilibrium. The galaxy looks frozen mid-relaxation, caught between chaos and calm. This is why Abell 2261 is more than just an interesting fact. It calls into question our whole picture of how galaxies evolve together. It has been found that the size of the core is related to the mass of the black hole that cut it. No, this one doesn't. It means that the scaling rules might not work at the very largest masses if its black hole really flew away. That could mean that the feedback between black holes and galaxies isn't as common as scientists used to think. High-resolution imaging reveals that the core's light distribution is slightly offset from the outer halo by several thousand light-years. That offset is small but statistically real, and it points in the same direction as the displacement seen in both the radio and X-ray maps. Such alignment across different wavelengths is unlikely to be coincidence. It suggests a single, powerful event, probably the gravitational recoil of a newly merged black hole, shifted the entire gravitational potential of the galaxy. The structure of the core is even more distinctive. The starlight isn't totally smooth. There are tiny ripples and bumpy areas that are left over from the collision that made the galaxy. These patterns might be tidal scars, which are signs of smaller galaxies being sucked in a long time ago, or they could be the marks of stars being thrown outward by a black hole as it leaves. If you could see the motion directly, you'd see circles that are all over the place, with some going around the center and others going off to great lengths. It's a traffic jam in space, caused by an explosion of gravity. Astronomers have run computer simulations to test this scenario. In the models, when two 10 billion solar mass black holes merge, the resulting recoil can displace the remnant by up to 10,000 light-years. The stars respond by expanding, creating a flattened brightness profile almost identical to what Hubble observes in Abell 2261. Over billions of years, the core should slowly contract again as gravity pulls everything back into balance, but that process takes time. The current shape could represent a snapshot just after the event, preserved because the galaxy is so enormous that dynamical friction acts sluggishly. The recoil plot twist. The most remarkable idea about Abell 2261's missing supermassive black hole sounds like something out of a movie, a cosmic reaction so strong that it threw a 10 billion solar mass monster out of its own galaxy. There is no such thing as science fiction. It is just general relativity gone crazy. You can feel changes in space-time when two black holes join. These waves are called gravitational waves. If these waves spread out haphazardly, the combined residue feels a kick, like a cannon firing a shell. As a result, at thousands of kilometers per second, the black hole speeds away from the center, pulling some of the stars closest to it along with it. The idea of a gravitational wave recoil isn't new. The math was first predicted decades ago, but it wasn't until Einstein's theory met the computing power of the 2000s that simulations revealed how extreme the effect could be. In the most energetic mergers, the recoil velocity can exceed 5,000 kilometers per second, fast enough to escape even a giant elliptical galaxy's gravitational grip. For comparison, the Milky Way's escape velocity is around 500. Such a kick could launch a merged black hole into intergalactic space, leaving behind a ghostly void where it once ruled. Abell 2261 fits the pattern perfectly. Its massive flat core could be the aftermath of just such a recoil event. In that scenario, two enormous black holes from merging galaxies spiraled together, ejected countless stars, merged, and then, because the gravitational waves weren't perfectly symmetrical, shot off in one direction, carrying a compact stellar cloak. The galaxy's core, suddenly deprived of its anchor, relaxed into the wide, flattened shape we see today. Even the offset between the optical and X-ray centers might trace the direction of the recoil. Astronomers call the cluster of stars bound to a recoiling black hole a hypercompact stellar system. It's basically a mini-galaxy orbiting an invisible gravity well. The stars move at blistering speeds, sometimes thousands of kilometers per second, producing broad spectral lines that give them away. If one of Abell 2261's bright inner knots shows those speeds, it would confirm the runaway theory overnight. So far, no such smoking gun has appeared, but the limits of our telescopes mean we might simply not have the resolution to see it yet. It's great that the recoil model can explain a lot of mysteries at once. The big lack of light, the core that isn't in the middle, and the fact that there isn't an active nucleus. After the black hole was released, it would no longer have any hot gas to feed on, so it would no longer be able to send out X-rays or radio waves. The Very Large Array would then see the relic radio lobes as the last faint echo of the quasar phase, which finished with the departure. The timing fits perfectly. Tens of millions of years ago, there was a bright period of jet activity. Then there was silence, and the gravitational heart moved. There's also evidence from other galaxies that supports the plausibility of such an event. In the galaxy 3C186, astronomers have found an active black hole that appears offset from its host by more than 30,000 light-years, moving away at nearly 2,000 kilometers per second. It's the best real-world candidate for a recoiling supermassive black hole, and it proves that these kicks can happen. If a smaller galaxy can launch its central engine, there's no reason a heavyweight like Abell 2261 couldn't have done the same, only on a grander scale. Of course, a recoil this powerful raises another question. What happens to the galaxy left behind? Without its central black hole, the inner stars lose their stabilizing force. Over time, the core expands and cools, matching what we observe. The missing black hole also disrupts feedback processes that regulate star formation and gas heating, potentially altering the entire cluster's thermal balance. In essence, the loss of a central black hole can change not just one galaxy, but its cosmic neighborhood. The Cloaked Runner. The black hole in Abell 2261 didn't move by itself if it really was kicked from the center. It would have pulled a small group of stars along with it, trapping the whole cluster in its strong gravity. This is a hypercompact stellar system, which is like a mini-galaxy that has gotten out of control and hides a huge star in its core. From Earth, it would look like a small bright knot of stars. But inside that bundle of stars, a black hole the size of billions of suns would bend space itself. This idea gives the search a practical target. Instead of hunting a black hole directly, which is impossible, you look for its disguise. You look for that stellar cloak, moving faster and shining slightly differently from the rest. In Abell 2261, 4 such knots stand out. Each one could, in theory, be the cloak. The most likely candidate lies just north of the galaxy's geometric center, positioned along the same direction as the offset seen in radio and X-ray maps. It's the perfect hiding spot for a black hole on the run. The expected signature is subtle but measurable. Stars bound to a supermassive black hole orbit at extreme speeds, thousands of kilometers per second. If one of the knots in Abell 2261 is such a system, its spectral lines should be dramatically broadened, the telltale fingerprint of high internal motion. Unfortunately, the galaxy is so distant that even Hubble's sharpest images can't resolve that motion directly. The light from each knot blends with surrounding starlight, masking any clear signal. It's like trying to spot a heartbeat from across a continent. Even so, researchers have tried. Using ground-based spectroscopy and adaptive optics, they've examined each knot's brightness, color, and composition. None show the high metallicity or strong ultraviolet excess you'd expect from a black hole heating nearby gas. They're old, red, and quiescent, typical of ancient stellar populations. Still, that doesn't rule out the possibility of a buried engine. A truly starved black hole wouldn't heat anything around it, leaving only its gravitational pull as evidence. The cloak hypothesis also explains why no single wavelength, X-ray, optical, or radio, has revealed the black hole yet. If the object carries its own star cluster, that envelope of stars and gas could absorb or scatter most of its emissions, turning the whole system nearly invisible. Only its internal dynamics, the speed of its stars, could betray its presence. That's why astronomers are now waiting for JWST and upcoming 30-meter class telescopes to measure those internal velocities directly. The instruments will be sensitive enough to detect the difference between an ordinary cluster and one harboring a 10 billion solar mass core. It would be amazing if a hypercompact star system in Abell 2261 were proven to exist. In addition to merging and recoiling, it would show that black holes can also live on their own and move between galaxies like celestial runaways. The galaxy's core is still not balanced because the gravity anchor has literally moved, taking part of its center of mass with it. Over billions of years, the stars in the core would slowly spread outward, making the huge flat light image we see now. There's another clue in favor of the cloaked runner scenario: the persistence of the offset. If the black hole had simply gone dormant, the surrounding stars and gas would have recentered over time. Instead, the displacement remains stable. The core's geometric center and the densest pocket of hot gas are both shifted in the same direction as the candidate knot. It's as if the galaxy is subtly leaning toward a missing weight, a gravitational pull felt but not seen. This isn't the first time astronomers have hunted a runaway black hole cloaked in stars. In the quasar CXO-J 101527, researchers found an active black hole displaced thousands of light-years from its host's center, still glowing faintly. But Abell 2261 would be the first case where the object isn't shining at all, only inferred through structure. Catching it would prove that the aftermath of black hole mergers can linger invisibly for eons, hidden inside star clusters smaller than a single pixel in our best telescopes. The stalled binary. Some people do not believe that Abell 2261's black hole left. Few scientists say it never really left. They say it's just stuck in an orbit with a partner it can't quite reach. This is the stuck binary theory, and it comes from one of the biggest astronomy mysteries. How do two supermassive black holes finish joining when they get close? When two galaxies collide, their central black holes sink toward the new center through dynamical friction, the gravitational drag created as they plow through stars and gas. They spiral together for millions of years, losing energy as they fling surrounding stars outward. That process continues until the pair is separated by a few light years. Then, the problem starts. Once the nearby stars are ejected, there's nothing left to drain the pair's orbital energy. The black holes stop sinking. Astronomers call this the final parsec problem, the point where a binary system stalls because the universe around it has gone quiet. If Abell 2261's black holes hit that wall, they could have been orbiting one another for billions of years without ever merging. The evidence fits. The galaxy's core is too wide and too smooth for a single quiet black hole, but too symmetrical for a recent ejection. A long-lived binary could have done exactly this. Slowly carve out the gigantic flat core by repeatedly flinging stars away while staying centered. Each orbit acts like a gravitational slingshot, clearing more space until the middle becomes a hollow plateau. Simulations of binary black holes show that this process can expand a galaxy's core by several thousand light-years, nearly matching what we see in Abell 2261. If the black holes are still there, separated by a few light-years, their combined mass could reach 10 billion suns. Together, they'd form a gravitational engine so massive that it shapes every star orbiting within thousands of light-years. But because they lack nearby gas to feed on, they'd remain dark, invisible to X-ray and radio telescopes alike. The stalled binary idea also explains why the galaxy's core looks offset but not chaotic. The black holes might be orbiting around a shared center of mass that doesn't line up perfectly with the optical center of the galaxy. Over time, that orbit could shift slightly, dragging the dense gas and stars into a new equilibrium, the faint asymmetry we see today. It's subtle but consistent with a massive unseen pair tugging on the galaxy from within. Astronomers have tried to test this scenario by searching for periodic signals. Two orbiting black holes should, in theory, cause small fluctuations in brightness or radio emission as their jets interact with surrounding gas. So far, none have been detected, but the signals could be too weak or too slow, taking thousands of years to complete a single cycle. At Abell 2261's distance, Even the most sensitive instruments might never see the rhythm. If it's true, it means more than one world. There would be a lot of stalled pairs in the universe. They would be leftovers from old mergers that got stuck at the last parsec. It's possible that these systems are waiting for new gas to fall in, another small merger, or even a passing star cluster to stir things up and force them to join together. When they finally do that, they'll send out bursts of gravity waves that will be strong enough for future devices like LISA to pick up directly. So, Abell 2261 could be a sneak peek at the next greatest event in the universe, but the story is stopped in the middle of a chapter. The sleeping giant. It's possible that the black hole in Abell 2261 never left or joined with another black hole. It could have just fallen asleep. The center black hole is still where it should be, according to the sleeping giant idea, but its engine has stopped working. It's not gone, it's just not working. After all, even the most powerful quasar runs out of fuel at some point. When the gas around the black hole gets too thin or too hot to fall in, accretion stops, light fades, and the black hole can't be seen. In the distant past, Abell 2261 could have been one of the brightest quasars in the cluster. Its central black hole would have devoured gas at near the Eddington limit, blasting out radiation and launching jets that shaped its entire galaxy. But as the fuel supply dwindled, those jets shut down. The X-rays disappeared, the radio glow faded, and all that remained was a massive black hole sitting in perfect darkness, a dead quasar, so quiet that even Chandra's X-ray vision can't pick it out from the background. Astronomers have caught other galaxies in this exact phase of cosmic burnout. In M87, the central black hole that once powered a mighty jet now glows weakly compared to its heyday. In NGC 1600, a galaxy of similar scale, the supermassive black hole weighs 17 billion suns but barely emits anything detectable. These monsters don't vanish, they just cool off, blending into the quiet centers of their galaxies. The same pattern could explain Abell 2261, an ancient engine now starved, surrounded by the leftover structure of its violent youth. If this is the case, we'd expect faint signs of past activity. And there are hints. The radio lobes detected by the Very Large Array, stretching tens of thousands of light years, tell us the galaxy once had jets. The morphology of those lobes, diffuse, fading and symmetrical, suggests they were powered long ago and then abandoned. They're the smoke trails of a once active core. Combine that with the galaxy's huge, hollowed-out center, and the story practically writes itself. The black hole had an intense feeding period, cleared its surroundings, and eventually starved. The thought of the sleeping giant works for the area too. The gas around Abell 2261 is very hot, tens of millions of degrees, because it is in the middle of a dense collection of galaxies. That kind of heat keeps new stuff from cooling down and dropping inside. It can't start up its accretion disk again if there isn't a steady flow of matter coming in. It stops radiating light, but still has a strong gravitational pull, like a light bulb that has lost its strength. It is still there, pulling, but in every wavelength we can see, it is turned off. To confirm this, astronomers are turning to the James Webb Space Telescope. Unlike Hubble or Chandra, Webb can see the faint infrared glow from dust and stars around a dormant black hole. If the core of Abell 2261 has even a trace of warm dust or disturbed starlight, Webb could detect it. The trick is separating the black hole's subtle imprint from the galaxy's bright background. It's not easy, but the telescope's precision offers the best chance yet of finding something where everything looks empty. Furthermore, it's possible that the black hole is still there, but that dust is covering it. Some galaxies hide black holes that aren't doing anything by thick clouds of matter that block both visible and X-ray light. They only show up in radio waves or infrared light. If this kind of cage is inside Abell 2261's core, the black hole might be slowly forming new matter at a rate that can't be seen by our sensors right now, but it's not really dead either. That whisper might be able to be picked up by future radio telescopes, like the Square Kilometre Array. the core that shouldn't exist. Astronomers didn't expect Abell 2261's heart to act the way it does, even though there isn't a black hole visible. Giant ellipticals should have thick, star-filled cores where gravity is strong, but the middle of this one looks like it was scooped out with a cosmic spoon. The few thousand light-years in the middle are strangely flat and empty. This galaxy has a core that is bigger than any other of its kind. Abell 2261 is one of the weirdest case studies in galactic organization just because of that one thing. The problem isn't just size, it's shape. Instead of tapering smoothly toward a bright center, the galaxy's brightness plateaus, staying constant across an enormous circular region before fading at the edges. In astrophysics, that's called a core-type profile, and it usually forms when a supermassive black hole, or a pair of them, ejects stars through gravitational slingshots during a merger. The bigger the core, the more stars have been flung out. By that measure, Abell 2261's missing stars suggest an ejection event of epic proportions. Yet there's a contradiction. If the black hole that carved out that space was still present, its gravity should pull the remaining stars inward and steepen the profile. Instead, the core remains smooth and relaxed, as though the central mass vanished. It's as if the galaxy completed its remodeling, then the architect disappeared. No accretion disk, no bright jets, no signs of central gravity stronger than the surrounding starlight. It's this mismatch between a core that requires a massive black hole to exist and the total absence of one that keeps scientists awake. To explain it, researchers have modeled dozens of scenarios. The runaway theory suggests the black hole was kicked out after merging. The stalled binary theory says it never merged, staying hidden and silent. The sleeping giant theory claims it's still there, but inactive. Each fits part of the evidence, but none perfectly. The core's extreme smoothness is especially troubling. Simulations show that after a recoil or binary clearing, the remaining stars should show ripples or asymmetries, yet Abell 2261's core looks like polished glass. Something more stable must have followed the chaos. One option is to refill the core. After stars were thrown out violently during a merger, the galaxy may have slowly pulled new stars in over billions of years, making the shape smoother. That means the merging took place a very long time ago, maybe when the universe was only half as old as it is now. The core we see now is the calm after a very old storm. The black hole might have gotten away or stopped working soon after, leaving behind a record of balance. We're not seeing an ongoing mystery then, we're seeing its long cold leftovers. However, even that calmness defies the odds. The central region of Abell 2261 measures over 10,000 light-years across, 5 times larger than the Milky Way's bulge. To create a void that wide, the original black hole system would have needed an almost unimaginable mass. Either the galaxy once hosted one of the largest black holes ever formed, or multiple giants merged there, hollowing out the core layer by layer. If so, Abell 2261 might be the ancient graveyard of several galactic hearts, not just one. The galaxy around it gives us more information. It has no tide tails or union scars that can be seen on the outside, which is smooth and lacks any features. That means the last big crash happened billions of years ago, which is long enough for the pieces to have settled down. Whatever moved the black hole wasn't recent. It happened a very long time ago. But that event's memory lives on in the galaxy's structure, from the flattened light curve to the tiny off-center radio bands that show where a nucleus used to burn. Researchers have even proposed that Abell 2261's core may represent a transitional phase, an intermediate step between active quasars and the quiescent giants we see today. In this view, it's a natural endpoint of galactic evolution. Over time, repeated mergers and feedback erased the dense centers of galaxies, leaving behind these vast calm voids. If so, Abell 2261 isn't an anomaly, but a preview of the far future for all massive galaxies, including our own. The galaxy cluster connection. You need to zoom out to really understand why Abell 2261's missing black hole is important. The Abell 2261 galaxy cluster is a busy city of galaxies held together by gravity and dark matter. This galaxy is not floating in space by itself. It is at the center of this cluster. That position in the middle is key. A giant black hole called the Brightest Cluster Galaxy, BCG, is found in almost every galaxy cluster that has ever been studied. It is the biggest galaxy in the cluster and acts like the power plant for the city. It controls the hot gas around it so that the cluster doesn't fall apart into chaos. The power plant doesn't seem to be there in Abell 2261 though. The Abell 2261 cluster lies about 2.7 billion light-years from Earth in the constellation Hercules. It's one of the most massive clusters known, holding thousands of galaxies and a vast reservoir of superheated plasma that glows in X-rays. At its heart sits the giant elliptical galaxy that gives the cluster its name, the one with the empty core. Normally, the central black hole in such a galaxy would keep the surrounding gas in check through a process called AGN feedback. As gas falls toward the black hole, it heats up and emits powerful jets and radiation, which push surrounding gas outward. That cycle prevents runaway star formation and keeps the cluster in balance. Chandra's observations show that the hot cluster gas near the center is strangely undisturbed. There are no bubbles, shocks, or cavities, features that active black holes usually carve into the surrounding plasma. Instead, everything looks placid. The gas density peaks right where the galaxy's optical light fades, as if nothing has been stirring it for eons. Without that feedback, the cluster's central atmosphere should have cooled and collapsed into new stars, but it hasn't. That quiet stability adds another twist to the mystery. The missing black hole's absence seems to have frozen the cluster in an unnatural equilibrium. Some researchers suggest that the cluster's dark matter halo is helping hold things together. Abell 2261's gravitational field extends for millions of light-years, with dark matter outweighing visible matter by at least 5-1. This invisible framework could stabilize the gas even without the central engine's help. If true, it implies that dark matter, not black holes, dominates the long-term evolution of cluster cores. The hot gas trapped in that halo could act as a buffer, keeping the region from collapsing while the black hole lies dormant or displaced. On the other hand, the stillness might be deceptive. If the black hole was kicked from the center, its energy injection could have ended abruptly, leaving the gas to settle slowly over time. The current calm might just be the afterglow of ancient turbulence. Radio maps hint at this. The fading lobes surrounding the core may be the last echoes of a time when the galaxy's nucleus was violently active, stirring the cluster's medium with colossal jets. When the black hole vanished or fell silent, the energy stopped, and the lobes began to fade. The cluster setting also gives the recoil scenario more weight. Galaxy groups are always combining, and the galaxies in the middle of them are where supermassive black holes are most likely to crash into each other. If Abell 2261's center black hole was thrown outward when two cluster galaxies merged, it might still be moving around in the cluster's gravity field. Since it is 2.7 billion light-years away, that moved core could not be found without very accurate tools. It could be tens of thousands of light-years from the center, moving around in the haze of the cluster without being seen. Astronomers are already testing this idea using cluster-scale mapping. The Hubble Frontier Fields and JWST surveys have begun searching for any faint compact X-ray or infrared sources near the cluster's core that could indicate a wandering nucleus. Nothing definitive has appeared yet, but the search area is vast. If found, it would be the first observational proof that a supermassive black hole can not only escape its host galaxy, but remain gravitationally bound to its parent cluster, a kind of cosmic refugee drifting among galaxies. The behavior of the intra-cluster gas also hints at timing. X-ray temperature maps show that the central region has been undisturbed for hundreds of millions of years, implying that the black hole's disappearance, or dormancy, happened long ago. That makes sense if the merger that created Abell 2261's current form occurred during the universe's Middle Age, when galaxy clusters were still assembling. The black hole might have been active during that time, shaping the early cluster before going silent or being expelled. The ancient collision. Going back billions of years to the time when galaxies crashed into each other is the only way to understand how Abell 2261 became so strange. Galaxies were not peaceful ovals of starlight back then. They were war zones. Gravity pushed systems together, smashing them into huge collisions that changed the way the universe is put together. There was a giant black hole in the middle of each of those galaxies, waiting for its twin. Because Abell 2261's core is so big and hollow, it's likely that it bears the mark of one of those past crashes. The galaxy we see today likely started as two giants, each with its own central black hole, billions of solar masses in weight. As they drew together, their halos of stars and gas collided first. Streams of dust lit up like fireworks, star formation exploded, and tidal tails stretched across hundreds of thousands of light years. It would have been one of the most luminous events in the early universe. Inside that chaos, the two central black holes spiraled toward one another, sinking into the heart of the new combined galaxy. Simulations show that during such a merger, the central region becomes violently unstable. Stars are slung outward at enormous speeds, evacuating the core. The process continues until the two black holes either merge or stall, leaving behind a cavity as smooth as glass. In Abell 2261, that cavity, over 10,000 light-years wide, is too large to be explained by anything less than a collision between supermassive black holes of extraordinary size. It's not the product of slow evolution or ordinary stellar migration. It's the signature of impact. If that merger truly occurred, it would also explain the strange offset between the galaxy's optical center and its surrounding X-ray gas. The collision would have shifted the center of mass slightly, tugging the remaining stars into a new configuration. Even the faint asymmetry of the light in Abell 2261's core fits the pattern of a long-ago galactic crash that has since settled into equilibrium. The colors of the galaxy's stars reveal that most of them formed over 10 billion years ago, meaning the merger likely happened early in cosmic history. Back then, galaxies were smaller but more gas-rich, ideal conditions for black holes to grow rapidly through accretion. When those galaxies finally collided, their central engines would have merged in a cataclysmic event, one that sent gravitational waves rippling across the cosmos. If we'd had detectors like LIGO or LISA back then, the signal from that merger would have been one of the loudest in the universe. But something about this collision must have gone differently. Either the black holes merged and recoiled, blasting out of the center, or they stalled and never finished. Both possibilities fit the evidence, and both would leave behind a galaxy like Abell 2261, vast, flattened, and disturbingly quiet. If the merger ended in recoil, the black hole could be wandering somewhere in the cluster right now. If it stalled, the pair could still be orbiting invisibly inside that empty heart, waiting for a nudge to bring them together. Even the cluster around it has signs of this violent past. It looks like the satellite galaxies around Abell 2261 are not spread out evenly, as if the edges of earlier collisions are still visible, and the hazy intra-cluster light, which is the soft glow between galaxies, might have stars that were thrown out when those galaxies merged so long ago. In this way, the galaxy's lost center isn't just a puzzle, it's proof of a cosmic event that changed the shape of a whole area of space. The Ghost Trail. If Abell 2261's black hole really did leave its home, it wouldn't have gone away completely. It would have left a weak but quantifiable mark of destruction in the galaxies around it. This is what astronomers call the Ghost Trail, a line of jumbled stars, gas and light that could lead right to the path of the missing monster. If they find it, they might finally know where the black hole went. When a supermassive black hole is ejected, it doesn't glide quietly. The recoil rips through its environment like a gravitational storm. Stars that were once orbiting peacefully around the galactic center are thrown outward. Dust clouds are compressed, twisted, and torn apart. For a brief cosmic moment, the galaxy becomes lopsided. its heart beats once, hard, and then goes still. The echo of that event can linger for billions of years in the form of faint asymmetries or displaced clusters of stars. That's exactly what some researchers think they've seen in Abell 2261. Hubble's deep imaging reveals that the starlight around the core isn't perfectly circular. It's subtly elongated toward one side, the same direction as one of the galaxy's mysterious knots of light, a candidate for a runaway black hole's companion cluster. The radio lobes, too, appear slightly offset along that same axis. To an astronomer's eye, these alignments are like footprints, faint, scattered, but consistent with a single fleeing source. The concept of following a ghost trail is relatively new in extragalactic astronomy, but it's proven powerful. In other systems, where a central black hole appears displaced, small gradients in stellar velocity or residual dust lanes have revealed the direction of motion. A black hole kicked at thousands of kilometers per second would have dragged a cluster of bound stars and gas behind it, like a comet's tail stretched across light years. Over time, that structure fades, but the gravitational scars remain. With advanced modeling, astronomers can rewind the motions of those stars and infer the kick's strength and vector, essentially reconstructing a cosmic crime scene from the debris. In Abell 2261, that reconstruction is underway. Using combined optical, X-ray, and radio data, scientists have simulated what the galaxy's core should look like if the black hole had recoiled northward a few thousand light-years. The result matches reality remarkably well. A flattened light profile, a small offset in gas density, and a lingering radio afterglow, consistent with an ejection that happened roughly 50 to 100 million years ago. That timescale fits perfectly with the fading radio lobes observed today. It's as if the black hole roared, leapt, and then went dark, leaving only turbulence in its wake. Still, confirming that trail is difficult. The features are incredibly faint, and the distance, 2.7 billion light-years, means even the best telescopes can't directly measure stellar motions in the core. Instead, astronomers look for indirect signatures, subtle color shifts caused by redder, older stars being left behind, while younger stars remain slightly displaced. The European Southern Observatory's Very Large Telescope and upcoming 30-meter telescope will soon be able to map those gradients in unprecedented detail. If a trail of accelerated stars can be traced in one direction, it would be the first tangible evidence that Abell 2261's black hole truly fled the scene. It's strange that gravity modeling also says that a kicked black hole would cause a ripple in the dark matter ring around it, which would slightly change the galaxy's overall potential well. This claim is being looked into by some experts to see if the galaxy's light distribution holds up. If the pattern stays the same, it means the recoil wasn't just a local event, but one that physically moved the galaxy's center of gravity, leaving a trace in the dark matter that can be measured. The black hole hunt. This question about Abell. 2261 has been at the center of one of the most frustrating astronomy studies for more than 10 years. On paper, the case looks easy. Just find the black hole that should weigh 10 billion suns. But after years of work, the core of the galaxy still has no X-rays, jets, or ultraviolet flares. Because there has been so much quiet, the search for Abell 2261's lost supermassive black hole has become like a modern-day detective story. Every major observatory is now involved in the study. The hunt began in earnest with Hubble's optical images, which first revealed the unusually large and smooth core. At the time, astronomers assumed the black hole was hiding near the faint knots of starlight visible in the center. But follow-up observations didn't show any of the subtle flickers or color shifts that would mark an active nucleus. So the search moved to higher energy. Enter the Chandra X-ray Observatory. If a supermassive black hole were accreting even the tiniest amount of gas, it would radiate in X-rays. Instead, Chandra saw nothing, a silence so complete that it ruled out any active galactic nucleus within a few thousand light-years of the center. The most powerful engine in the cluster appeared completely dead. To make sure the signal wasn't just faint, Astronomers stacked multiple exposures, stretching their detectors to the limit. Still no trace. For a while, the idea of a missing black hole seemed almost unthinkable. Then, radio astronomers stepped in. The Very Large Array mapped the same region and detected two vast lobes of ancient radio emission, the faint fingerprints of past jet activity. The symmetry and orientation of those lobes suggested that a black hole once sat between them, feeding energy into the cluster tens of millions of years ago. But the core that powered them was now cold. The galaxy's center no longer glowed in radio frequencies, meaning the jets had long since shut down. The timing of that shutdown matched the timescale for a potential black hole ejection, around 50 to 100 million years. Astronomers began scouring archival surveys, looking for faint off-center radio or X-ray sources elsewhere in the cluster that might betray the runaway. A few candidates surfaced, small, compact spots of radiation within 10,000 light-years of the core, but none showed the energy levels expected from a black hole of that size. The most likely explanation: either the object is completely dormant, or it has moved so far from the center that it now drifts through the cluster's hot gas, invisible to our instruments. Next came the Hubble spectroscopic survey, measuring the velocities of the stars inside the core. If the black hole was still present, even inactive, its gravity would cause a spike in stellar speeds near the center. Instead, the velocity field is surprisingly flat. That doesn't necessarily mean the black hole is gone. Its immense mass could be smoothed out across a wide region, but it strengthens the argument that something truly unusual happened here. Either the black hole left, or it sits hidden in an unexpected place, wrapped in a cluster of stars that conceals its pull. The search has moved into a new era. Older telescopes couldn't see the infrared light that comes from warm dust or gas that is slowly accreting, but the James Webb Space Telescope can. Its sensitivity could show a black hole that isn't active by the faint heat it gives off, or the changes in the orbits of close stars that it causes. Webb's first look at Abell 2261 is expected to push the limits of what can be found to levels that have never been seen before. If there's even the faintest hint of movement, it should pick it up. The Laser Interferometer Space Antenna, LISA, which is scheduled to launch in the 2030s, could find gravitational waves coming from pairs of black holes rotating in large galaxies like this one. LISA might hear the slight rumble of a binary star still stuck in Abell 2261 long before any light leaves. And if the black hole really did release matter, LISA's data could help find other places where this has happened, showing that runaway giants happen more often than we thought. The evidence buried in light. There are times when the best hints aren't in new findings, but in the faint traces that are already buried in old data. Astronomers have started looking over all the pixels of stored light from Abell 2261 again, this time looking for the tiniest differences that could mean there is a black hole there. It's taking a while, but the results are slowly showing something amazing. The proof may have been out in the open the whole time. On the surface, the galaxy's light profile looks like it came from a book. It is smooth, even, and spread. But when scientists digitally take away the outer glow and focus on the first few thousand light years, small differences start to show up. On the northwest side of the core, there is a soft gradient that makes it just a little bit lighter. Not only is it clear in raw pictures, but it also shows up as a faint blur in residue maps, which is exactly where earlier research suggested the black hole might have gone. The signal could be moonlight from a close-together cluster that is held together by an unseen mass. To test that, astronomers compared the color of this region with the surrounding core. The inner glow is slightly redder, suggesting older stars and a denser population. That makes sense if the area contains a gravitationally packed cluster, a remnant shell of stars dragged along by a recoiling black hole. The distribution isn't random. It lines up perfectly with the axis of the ancient radio lobes, as though the whole structure remembers which way the galaxy's heart once pointed before it went silent. But light can tell more than shape and color. It can tell motion. Using spectral line analysis, scientists looked for Doppler shifts in the starlight across Abell 2261's core. The differences are small, tens of kilometers per second, but they show a hint of rotation near the region of interest. That motion isn't expected in a static symmetric core. It implies gravitational influence from something massive just beneath the noise threshold. It's not proof, but it's a fingerprint. Even the galaxy's faintest light holds secrets. Observations from the Subaru telescope and the Hubble Frontier Fields program detect a diffuse envelope of intra-cluster light around Abell 2261, starlight that doesn't belong to any single galaxy. The density of that halo peaks slightly off-center from the galaxy's optical heart, again along the same axis. This could be coincidence, but it could also mark the faint trail of stars torn away as the black hole and its cluster moved outward. If that's true, the evidence for a recoiling core isn't gone. It's written in starlight smeared across space. Computer models have caught up with the data. When researchers simulate a black hole merger followed by a recoil kick, they can reproduce the peculiar brightness and symmetry of Abell 2261 almost exactly. The key parameter is the timing. If the ejection happened around 100 million years ago, the disturbed stars would have had just enough time to smooth out their motions, leaving the faint residuals we see today. Any older, and the clues would have disappeared completely. Any younger, and the asymmetry would still be sharp. The fit is uncanny. Abell 2261 looks like a galaxy frozen right at the sweet spot where the memory of its missing black hole hasn't yet faded. The star streams around the void. In the middle of Abell 2261, if you zoom in far enough, you won't see chaos, but order where there is none. Astronomers who are studying how the galaxy's stars shine have found something that shouldn't be there. Thin streams of stars smoothly curving around what appears to be nothing. These small arcs and slopes might be the only visible sign of a gravitational force that can't be seen anymore. They could be the supermassive black hole's ghost mark. Star streams like these aren't ordinary. In spiral galaxies, you might see similar arcs created by tidal interactions with satellites. But Abell 2261 is an enormous elliptical, long past the stage of active collisions or tidal disruption. Its stars should be random, scattered, and old. Instead, high-precision models show that the velocity field in the core region contains ordered motion, small but consistent deflections, like orbits around a center that isn't there anymore. That pattern suggests one thing. There was once a powerful gravitational anchor, and its influence still guides the remaining stars. Researchers at the University of Colorado modeled what would happen if a 10 billion solar mass black hole was suddenly ejected from such a system. The results were eerie. Within a few million years, the densest stars around the center would begin to drift outward, but not randomly. They'd maintain partial orbits, forming elliptical flows that wrap around the central void like a gravitational whirlpool. These streams would fade over time as stars disperse, but for tens of millions of years, their arrangement would still echo the presence of the vanished core. The current pattern in Abell 2261 matches that time frame almost perfectly. Spectroscopic measurements add more intrigue. While the average motion of stars across the galaxy's heart appears flat, regions along one axis show velocity deviations of nearly 40 kilometers per second, a small but significant wobble. That's exactly what you'd expect if some of those stars are still following the gravitational pathways left behind by a recoiling or stalling black hole system. In effect, they're tracing ghost orbits, continuing to move under the influence of a mass that may no longer be there. When you look at Abell 2261's light profile next to those of galaxies that still have black holes at their centers, you find one of the most surprising results. In simulations where the black hole stays, the stars around it finally flatten out into a sharp center brightness spike. But when a galaxy's black hole is released, the core doesn't just flatten, it creates a density ring, a faint shell where stars that have been pushed out briefly gather before spreading outward. In Abell 2261, tiny streams were found that match that structure. This suggests that the galaxy's core may still be recovering from a huge gravity blow. Even the color of those stars helps tell the story. The faint arcs surrounding the void are slightly redder than the outer halo, indicating older stars, the same ones that once orbited close to the center before being flung outward. They've aged quietly in the aftermath, orbiting through the ghost of what was once the most powerful object in the cluster. It's as if the galaxy's ancient citizens are still moving through the memory of a king that's no longer on the throne. This lingering motion could also explain why the core remains so abnormally smooth. The gravitational tides from an ejected black hole would have been strong enough to erase smaller irregularities and scatter low-mass stars evenly, creating the broad, flat profile we see today. Over time, these streams would blend into the general stellar population, leaving behind only the faintest kinematic fingerprints. The fact that we can still detect them means the ejection or merger that caused them is relatively recent in cosmic terms, probably within the last 100 million years. The weight of nothing. The strangest thing about Abell 2261 isn't what's there, it's what isn't. When astronomers calculate how much mass the galaxy's gravity should have, the numbers don't add up. The stars and gas account for most of it, but not all. There's a missing chunk, roughly the same mass as a 10 billion solar mass black hole. It's as if the galaxy's books were balanced for an object that no longer exists, a gravitational debt that refuses to be erased. In normal giant ellipticals, this invisible mass sits right at the center, dominating the orbits of nearby stars. Astronomers can measure it by tracking how fast those stars move. The tighter the orbits, the heavier the hidden mass must be. But in Abell 2261, that central pull is muted. The stars drift slowly, almost lazily, as though gravity at the core has weakened. The numbers point to an absent anchor, not destroyed, not collapsed, just missing from the spot where it should be. To make sure nothing was overlooked, researchers modeled the galaxy's dynamics in exquisite detail. They used data from the Hubble Space Telescope, the Subaru Observatory, and Chandra, building a 3D map of its gravitational potential. Every version of the model required a black hole of at least 10 billion solar masses to explain the outer velocity field. Yet when they placed that mass in the center, the simulated starlight became too concentrated compared to what's actually seen. In other words, the galaxy behaves like it has a supermassive black hole's worth of mass. But the light says it's gone. This paradox has led to one of the strangest conclusions in recent astrophysics. Abell 2261's missing black hole has left a measurable gravitational footprint without leaving a trace of itself. The galaxy's stars and gas still move as if they're adjusting to an absence they can feel but not see, like ripples after a stone has been pulled from water. Theorists describe this as a mass deficit, a lingering echo of the force once exerted by the black hole before it vanished or went dormant. Some scientists think the deficit might not mean the black hole left entirely. Instead, it could be spread out, hidden in a diffuse, low-density envelope, a structure formed if the black hole dragged nearby material as it recoiled. That scenario would create an extended region of gravity that looks like nothing, yet still weighs billions of suns. Detecting it would require tracing tiny variations in the motions of stars and gas, something that next-generation telescopes might finally manage. Some people have a more extreme view. Some of the mass that is missing might have been moved into the cluster around it through gravity forces, they say. When two galaxies join with enough force to push out a black hole, energy is pumped into the stars around it, pushing them outward and changing the cluster's overall mass distribution. If that really did happen here, Abell 2261's weight loss is happening all over millions of light years. The black hole didn't go away. Instead, it sent shock waves of gravity through the cluster. Then there's the possibility that the hole is still there, but gravitationally quiet. In that case, the deficit would be an illusion caused by the galaxy's smooth brightness profile. A central black hole that's starved of matter emits no radiation, so it leaves no direct signature. only its pull would betray it. And if its influence has been diluted by a previously ejected companion or a flattened star field, even that pull could be subtle enough to hide. The aftermath in the gas. Every galaxy lives through its gas, which is the unseen stuff that gives stars energy, feeds black holes, and sends out waves across the electromagnetic spectrum. That breath is no longer heard in Abell 2261. The intracluster gas around the heart of a brightest cluster galaxy usually glows brightly in X-rays, but it is calm, smooth, and seems to be untouched. It's like the galaxy's lungs are no longer getting bigger, and the silence itself tells us what happened after the black hole went away. Typically, when a central black hole is active, it blasts its environment with high-energy radiation and powerful jets. Those outflows push hot gas away from the center, creating cavities and bubbles visible in X-ray maps. When the activity stops, the gas begins to flow back in, cooling and collapsing toward the core. In Abell 2261, though, neither effect is visible. The X-ray data from Chandra show no cavities, no shocks, and no signs of a cooling flow. The hot gas just sits there, still, uniform, indifferent. That absence of disturbance is actually remarkable. It means the black hole, if it was ever there, has been inactive for tens of millions of years, maybe longer. The radio lobes nearby, vast faint shells of emission, tell us that powerful jets did exist once. They must have inflated those lobes, heating the surrounding plasma and sculpting the intra-cluster medium. But those jets have long faded, and the gas has had enough time to settle back into equilibrium. The timeline matches the most likely recoil period, roughly 100 million years since the black hole's last active phase. The gas's temperature can also tell you something. The X-ray spectrum shows that it's about 30 million Kelvin, which is normal for cluster cores but not normal for the first 50,000 light-years. It is normal for the temperature to drop toward the center. This is where gas cools and falls in, filling the black hole. The decline is not there in Abell 2261. It seems like something equally heated the gas a long time ago and then stopped, leaving a quiet that hasn't changed. That something could only have been a strong quasar wind or jet, which can only come from a supermassive black hole. This frozen gas halo also offers indirect support for the recoil scenario. When a black hole gets kicked out of a galaxy, the jets vanish almost instantly. The sudden shutoff halts the inflow and leaves the surrounding plasma stranded, still hot, but no longer replenished with energy. Over tens of millions of years, that plasma cools uniformly, erasing any sign of turbulence. The smoothness of Abell 2261's X-ray halo is exactly what such a recoil aftermath should look like. A system that lost its central engine mid-sentence and never recovered. If the black hole was ejected only partially, say, kicked a few thousand light-years but still gravitationally bound, it might now be ploughing through the cluster's hot atmosphere, dragging a wake of disturbed gas behind it. Astronomers have started looking for such miniature shock fronts or compressed regions in the X-ray maps, faint ripples that might trace its path. So far, nothing definitive, but the idea is promising. The gas is an excellent detective. It records every passing force, every gust of energy. A displaced black hole would leave its fingerprints in subtle pressure gradients that next-generation X-ray telescopes could detect. There's also the question of metallicity, the concentration of heavy elements in the gas. In most massive galaxies, the innermost plasma is enriched by repeated cycles of star formation and black hole-driven winds. In Abell 2261, the core's metallicity is lower than expected, another hint that something disrupted the recycling process long ago. The lack of new stars and the absence of enriched outflows both point to a system that's been dormant since its last major merger. No recent activity, no chemical renewal. The galaxy is, in a sense, frozen mid-breath. The echo of radiation. Even though Abell 2261 doesn't seem to be doing anything right now, there is still a faint old light floating through space. It's an afterglow from the time when its missing black hole shone like a star. You can't see this radiation return with the human eye or even with one telescope. There are weak, stretched-out photons that used to come out of the galaxy's core when it was a quasar that carry it into the background of the universe. Astronomers are learning how to find these dying power sparks right now, and Abell 2261 could be the perfect fossil to test the method. When a supermassive black hole feeds, it floods its surroundings with radiation, ultraviolet, X-rays, and radio waves. When it stops, that radiation doesn't vanish instantly. It fades, cools, and travels outward for millions of light years, scattering through dust and intra-cluster gas. Some of it becomes trapped in the plasma's magnetic fields, re-emitted later as diffuse radio light. Others bounce between gas clouds, slowly reddening as the universe expands. The total sum of all this fading energy is called AGN relic emission, a kind of cosmic echo chamber for galaxies long gone quiet. In Abell 2261, this relic energy is still faintly detectable. The Very Large Array and LOFAR, the low-frequency array in Europe, have both captured an extended glow of low-frequency radio waves enveloping the central galaxy. It's too weak to be powered by current activity, meaning it's leftover light, a ghost signal from when the black hole's jets were still roaring. The shape of this glow forms two soft lobes aligned perfectly with the axis of the galaxy's core, like smoke plumes frozen in time. They stretch across more than 100,000 light-years, evidence that the nucleus once generated enough energy to affect not just its host galaxy, but the cluster around it. Astronomers can actually age-date this relic radiation. Electrons producing the radio glow lose energy over time, bending the spectrum toward lower frequencies. By measuring that curve, scientists estimate when the jets turned off, about 100 million years ago, matching the suspected timing of the black hole's ejection or shutdown. It's the clearest chronological link yet between the galaxy's calm present and its violent past. When a quasar phase ends, the hot gas it once illuminated stays ionized for thousands of years before recombining. That process leaves behind weak X-ray emission, often elongated along the same direction as old jets. In Abell 2261, Chandra detected just such a faint asymmetry, a whisper of extra brightness on one side of the core. It's not enough to confirm an active source, but it's perfectly consistent with residual heat from long-dead radiation fronts. And even in visible light, a trace lingers. Deep imaging has revealed diffuse arcs of faint blue starlight stretching through the cluster's center. These aren't young stars. They're old ones reflecting off intracluster dust, which itself was heated by ultraviolet quasar light eons ago. Those tiny reflections still carry the memory of the galaxy's brightest era, like embers glowing at the edge of a vast cold fire. Scientists are now trying out stacking methods, which involve putting together several long-exposure pictures from different wavelengths to make these old signals stronger. The Square Kilometre Array and the Lynx X-ray Observatory will make it possible to find even fainter echoes in the coming years. They will figure out when and how the black holes in galaxies like Abell 2261 turned off by drawing a picture of how radiation fades from those galaxies. That is, they will make it possible for us to see the light die slowly. The dark matter cage. Beneath the stars, gas, and light of Abell 2261 lies something far more dominant, an enormous dark matter halo, invisible but responsible for holding the entire galaxy cluster together. While we can't see it directly, its influence defines everything, from how galaxies orbit to how gas flows and cools. And in Abell 2261's case, that invisible web might be the key to understanding how its black hole vanished, or where it's hiding now. Dark matter makes up about 85% of all matter in the universe, and every massive galaxy sits inside a halo of it. For a brightest cluster galaxy like Abell 2261, that halo spans millions of light years. It's smooth and spherical on the outside, but denser toward the center, forming what astronomers call a gravitational potential well. Think of it as a cosmic basin. Stars, gas, and even light fall into it, bound by the invisible pull. When two galaxies merge, their dark matter halos merge too, colliding like clouds of fog, slow and diffuse but powerful enough to reshape space itself. In simulations of galactic mergers, these dark matter interactions play a crucial role in what happens to the central black holes. As the galaxies fuse, the overlapping halos create gravitational drag, helping the black holes sink toward the center and eventually merge. But if the halos are unusually symmetric or too diffuse, that drag can weaken. In that case, a merged black hole can escape more easily if hit by a gravitational recoil. Abell 2261 fits this scenario perfectly. A massive, smooth halo that could have allowed its supermassive black hole to slip free after a merger, unimpeded, like a marble gliding through honey. Astronomers studying Abell 2261's gravitational lensing, the bending of background light by mass, have mapped its dark matter distribution in detail. The results show that the cluster's core has an unusually shallow density gradient. Instead of a steep peak at the galaxy's center, it flattens out, mirroring the flattened starlight profile. That suggests the black hole's ejection might have literally reshaped the dark matter, carving out a small dip in the middle of the potential well. In other words, when the black hole left, even the invisible matter felt it. Some researchers proposed that the black hole might not have escaped entirely. Instead, it could be orbiting within the halo itself, gravitationally bound to the cluster but far from any single galaxy. A 10 billion solar mass object drifting through dark matter would generate tiny distortions in the cluster's gravitational lensing signature, subtle warps in the images of background galaxies. Future instruments like the Nancy Grace Roman Space Telescope and Euclid are designed to detect exactly those warps. If they spot a small, localized lensing anomaly near Abell 2261, it could reveal a wandering black hole cloaked in darkness. The interplay between dark matter and black holes goes both ways. While dark matter affects how black holes move, black holes also affect how dark matter clumps. The intense gravity of a central black hole can pull dark matter inward, steepening the density profile near the core. When that black hole is removed, through ejection or merger, the remaining halo relaxes, redistributing mass and flattening the core. That feedback mechanism may explain why Abell 2261's dark matter halo and its stellar core look so similar. Both have been smoothed by the same event, the loss of a central gravitational anchor. Understanding that connection could answer a deeper question, whether dark matter is truly collisionless or if it interacts weakly with itself. If the halo around Abell 2261 shows patterns of self-interaction, it might explain why its central region stayed so round after such a violent event. Instead of collapsing inward after the black hole's removal, the halo remained cushioned, redistributing its energy like a fluid. That would support emerging theories that dark matter isn't completely inert, that it might scatter or self-adjust under extreme conditions. Another worrisome option is that the lost black hole may have caught a small pocket of dark matter during its recoil and pulled it along with it as a gravitational cocoon. If that were true, the black hole wouldn't be moving by itself. It would be pulling a thick mass that we can't see with it. It's possible that the clump is still interacting with the halo of the cluster, causing faint, moving changes in the background light that could one day be found by advanced lensing studies. The runaway scenario. If the lost supermassive black hole from Abell 2261 really did leave its galaxy, then a 10 billion solar mass monster is still moving through the cluster's empty space. It is silent, cold, and can't be stopped. The runaway situation is one of the most exciting things that could happen in science. It imagines a black hole that has been kicked out of its home galaxy and is now moving through intergalactic space with only a few stars and dark matter following it around like adoring fans. Simulations of gravitational recoil events make this scene surprisingly plausible. When two supermassive black holes merge, the gravitational waves they emit aren't perfectly symmetrical. If more energy is radiated in one direction, the the merged remnant recoils in the opposite direction, a gravitational rocket effect. Depending on the masses and spin alignments of the black holes, that kick can reach thousands of kilometers per second, more than enough to launch the new black hole beyond the galaxy's escape velocity. Once free, nothing can stop it. It drifts indefinitely through the cluster, invisible except for the faint cluster of stars it carries with it. For Abell 2261, this picture fits too neatly to ignore. Its massive flattened core looks exactly like what's left when a black hole has been ripped away. The radio lobes show that it once powered enormous jets. The symmetry of the X-ray halo suggests the disturbance happened millions of years ago, long enough for the galaxy to settle, and the offset light knots near the center could easily be the star cluster that went with the black hole when it was expelled, a hypercompact stellar system orbiting an invisible engine as it flees through the cluster's hot plasma. If such a runaway exists, it wouldn't be entirely dark. The intergalactic medium in a galaxy cluster isn't empty, it's full of thin, hot gas. A moving black hole plowing through that medium would create a bow shock, compressing and heating the gas in front of it. That shock could emit faint X-rays or radio waves, a glowing trail that marks the black hole's passage. At the same time, its stellar cloak could shine faintly in optical light, looking like a tiny, fast-moving galaxy only a few hundred light-years wide. Spotting one would require extreme resolution and luck, but the physics says it's there. The search is already underway. Teams using the JWST and the Subaru telescope are looking in the area around Abell 2261 for small off-center sources moving in strange ways. Finding an object whose stars move thousands of kilometers per second instead of hundreds of kilometers per second is the trick. That signature would show right away that the gravity pull is coming from a secret black hole. Small, dim sources, a few thousand light-years from the physical center of the galaxy, have already been pointed out as possible possibilities. While none of them have been proven yet, they all seem to be very close to the path that recoil models suggest. If detected, a runaway black hole would be a cosmic first. We've seen stellar mass black holes kicked out of supernova remnants before, but never a supermassive one. Such a discovery would rewrite how we understand galaxy evolution. It would mean that black holes aren't just the hearts of galaxies. They can become their ghosts, roaming freely through space. Every merger, every quasar, could potentially launch one of these intergalactic wanderers, each carrying the ashes of a galaxy long gone. Additionally fascinating is the idea that these black holes could start new galaxies. They slowly build small systems as they move by pulling gas and stars around them. A moving black hole could gather enough matter over billions of years to create a weak, dwarf-like galaxy that orbits far from any cluster core. So what if Abell 2261's lost heart really did get away? It could be quietly shaping one of those ghost galaxies in the space between worlds. The runaway situation is both alarming and majestic for the experts who are looking into this case. It means that the world isn't always the same. Even the biggest, most stable objects can lose their cores, and gravity's strongest holds can break. A thing the size of our solar system, but heavier than 10 billion suns, could be moving through space in silence, without being seen but unable to be stopped. It would change any gas it meets into something new. The Wanderer's Trail. If Abell 2261's runaway black hole is really out there, it didn't just disappear, it left clues. It leaves a weak trail through the cluster for every gravity pull, every wisp of gas it stirs up, and every star it pulls off course. This type of proof is known as a dynamical wake by astronomers. It is a long, unseen ripple that big objects leave behind as they move through space. Telescopes may now be strong enough to find one for the first time. When a black hole of that scale moves through the hot plasma of a galaxy cluster, it pulls matter toward it, like a ship carving through water. The displaced gas compresses and heats, creating a trail of denser, hotter material. Over millions of years, that wake can stretch across tens of thousands of light years. In X-rays, it would appear as a narrow ridge of faint brightness. In radio, as a subtle stripe of polarized emission. No one has yet confirmed one from a runaway supermassive black hole, but Abell 2261 might give us the first chance. New simulations from NASA's Goddard Space Flight Center show what such a trail would look like. If the black hole was kicked northward at roughly 3,000 kilometers per second, its path would intersect the edge of the galaxy's inner gas halo, where the density changes sharply. The result would be a thin, curved ribbon of slightly hotter gas, persistent for about 100 million years before fading. Intriguingly, Chandra's deepest X-ray exposure already hints at a weak linear feature running just north of the galaxy's center. It's barely above the noise, but it's exactly where models predict the runaway's path should begin. At optical wavelengths, the wake could look different. As the black hole drags its mini-star cluster through space, its gravity can slingshot nearby stars, tossing them into thin arcs. These stellar streams would fan out over thousands of light years, faint but detectable with next-generation instruments. The JWST's NIRCam and the upcoming Nancy Grace Roman Space Telescope have the resolution to detect those diffuse arcs, especially if they reflect the faint glow of the intracluster light. Finding one aligned with the suspected recoil direction would be the smoking gun, a physical trace of a supermassive black hole on the move. The idea of a gravity lensing path is even unsettling. A black hole as big as Abell 2261's that gets out of control would slowly bend space along its path, making the light from nearby galaxies look funny. These changes would be very small, tiny lengthenings that could only be seen with statistical analysis, but they might line up with the expected wake. The Hubble Frontier Field's data are already being used by a group to look for those signals. If they can find a group of lensing oddities that make sense, it would be the first indirect proof that a giant black hole can pull space-time behind it. Of course, detecting any of this is brutally difficult. The galaxy cluster's own background noise, hundreds of galaxies, tangled magnetic fields, turbulent gas, masks faint features easily. But the search is narrowing. The region north of Abell 2261's core now stands as the most likely hunting ground. If a wake is confirmed there, astronomers can follow it outward like detectives tracing tire tracks from the scene of a crash. Somewhere along that line may lie the black hole itself, still carrying its tiny escort of stars through the haze. If someone found a moving trail, it would not only solve this puzzle, it would also start a new field of study. It's possible that runaway black holes will be able to be identified by the marks they leave on gas and light. There may be clusters of these unseen explorers all over the universe. Each one leaves behind small marks on the places it goes. Abell 2261 could be the first place we prove it. Its quiet core, offset radio lobes, and faint directional features all point to motion, to something heavy that once moved and never came back. If astronomers confirm that a wake exists, it will mean the impossible happened. A galaxy's heart got up and walked away, and space itself still remembers the way it went. The search beyond the cluster. The black hole from Abell 2261 is no longer connected to its home galaxy or even the cluster around it if it has reached full escape velocity. It would now be floating around in the space between galaxies, a cosmic refugee lost in the dark. That idea has led to a new area of astronomy, the search for giant black holes that are far from any other galaxies and float in space by themselves. For decades, such objects were considered impossible to detect. Without surrounding stars or gas, a black hole emits nothing, just an invisible gravitational field. But astronomers have begun to realize that even the loneliest giants can give themselves away. As they travel through the thin gas between galaxies, they leave trails of shocked material that glow faintly in radio and X-ray light. Occasionally, they might even trigger brief flickers of accretion if they pass through a denser patch of intergalactic gas. These emissions would be faint, billions of times weaker than an active quasar, but detectable by sensitive arrays scanning for diffuse, transient signals. The search for such wanderers began in earnest after Abell 2261. If its black hole escaped, then others probably have too, Clusters are violent places where galaxies collide frequently, and each merger is a chance for a recoil event. Statistically, there should be hundreds of rogue black holes drifting through space within a few billion light-years of us. Astronomers call them intergalactic seeds, the ghosts of mergers past. Some may still carry faint stellar halos, others may have been completely stripped bare. If found, they'd prove that black holes can survive exile and keep shaping the universe long after leaving their birthplaces. To find them, researchers are combining data from multiple observatories. The Vera Rubin Observatory, set to begin full sky surveys soon, will scan for tiny, fast-moving patches of light, objects that shift slightly against the background stars over months or years. These could be the faint stellar clusters bound to runaway black holes. Meanwhile, the Square Kilometre Array, SKA, will hunt for diffuse radio emissions consistent with bow shocks in the intergalactic medium. The Erosita X-ray telescope is mapping nearby clusters in search of off-center, wandering point sources that can't be matched to any known galaxy. Together, these instruments form the most coordinated black hole search in history, one inspired directly by the mystery of Abell 2261. There have already been some enticing hints. Scientists using the Chandra X-ray Observatory and the Canada-France-Hawaii telescope found a strange, small source of light 230,000 light-years away from a galaxy in a different cluster in 2021. It wasn't a normal galaxy because it moved too fast and didn't shine bright enough. Spectroscopic studies showed that it was a very dense group of stars circling a very massive, unknown core. The core could be a black hole 3 million times the mass of the Sun that was thrown out a long time ago. Even though it's not as big as Abell 2261's lost monster, it shows that black holes can go crazy. If Abell 2261's black hole truly escaped, it might still be detectable the same way. Astronomers estimate it would be about 10,000 light-years away from its galaxy by now, moving through the cluster's outskirts. Its gravitational influence would slightly distort the motions of nearby galaxies, a deviation precise enough for future missions like Gaia-Near to measure. And if it carries even a few hundred stars, those stars would emit just enough light to appear as a faint, fast-moving dot in deep-field imaging, something that could already be hiding in J.W. Estes data, waiting for someone to notice. It would help solve more than one puzzle if you could find it. It would create a new type of space object, intergalactic wanderers. These are black holes that are not part of any galaxy but still bend space wherever they go. As their tracks are shaped by the unseen web between galaxies, they might even be useful for making maps of dark matter. And if Abell 2261's black hole is one of them, then right now, somewhere in the constellation Hercules, a gravity giant is speeding through time and space by itself without being seen. With each passing light year, it makes a small change in the way space-time works. It might never go back home, but it still has an effect on the area it used to rule. The galactic heartbreak. If you take away the science, what happened in Abell 2261 is almost poetry. It was a huge cosmic sadness. Galaxies and black holes eat off of each other and shape the futures of each other. This one had a partner for billions of years. Its center black hole, the gravitational soul that held the balance, shaped the light, and organized the stars. Then that link broke one day. The black hole either ran away or stopped talking, leaving the galaxy empty and sad. That loss didn't just change its appearance, it rewrote its identity. The flat, calm center that puzzles scientists today is really a wound. Every orbiting star, every patch of hot gas still carries the memory of a pull that's no longer there. The galaxy moves on, but slowly, clumsily, like a dancer missing its partner. Even the faint asymmetries we see, the slightly off-center glow, the curved streams of stars, could be echoes of that cosmic separation, frozen in motion. In astrophysical terms, Abell 2261's heartbreak was inevitable. Mergers are messy. Galaxies crash, black holes collide, And when the energy released by that union unbalances the system, something has to give. Sometimes it's a few billion stars flung outward. Sometimes it's the black hole itself, kicked away by the very space-time waves it created. The moment it left, the galaxy's equilibrium collapsed like a house of cards, the remaining stars relaxing into the smooth, featureless plateau we see today. That smoothness isn't calm, it's aftermath. The cluster around this split also changed. The area cooled, became stable and darkened because there was no active center to pump energy into the intracluster gas. The galaxies next to it also lost the tug of war that held them to the brighter center of the cluster. Millions of light years away, that one disappearing object left, effects that show how one black hole, even if it's unseen, can change the mood of a whole area of space. There is something disturbing and relatable about that thought. Galaxies and black holes are often thought of as two different things, one made of stars and the other of shadow, but they really grow as a single organism. The galaxy feeds and guards its heart, while the black hole controls how big the galaxy gets. Not only is the end of that relationship a big deal, but it's also the end of balance. Abell 2261 is the picture of a galaxy that is trying to figure out how to live without its center. And yet, that silence isn't meaningless. It's part of a larger story, a cycle of death and rebirth written across the cosmos. If the black hole truly escaped, it may one day encounter new gas clouds, rekindle its accretion, and light up again as a quasar in another corner of the cluster. If it remained dormant within, new mergers or infalling matter could awaken it once more. Even heartbreak, in cosmic terms, is temporary. Scientists also think that might be possible. They made a model of how black holes that have been asleep can wake up when they get new gas from moving galaxies. If Abell 2261 ever joins with itself again, its quiet center might come back to life. It might not be as bright as before, but it would be enough to show the cluster that its heart is still beating. That flash in the future could happen today or in 10 billion years. Time in the universe doesn't heal fast, but it always goes forward. For now, Abell 2261 stands as a symbol, not of loss, but of change. Its hollow center is a testament to how dynamic galaxies truly are, and how even absence can have gravity. Every pixel of light from it is a love letter to a missing heart. Every photon a message that says, something powerful was here once, and the universe still remembers. The black hole that could return. The nothingness of Abell 2261 may seem like the end of the story, but stories in cosmic history are rarely left unwritten. There is a good chance that the galaxy's lost supermassive black hole won't stay gone forever. It might come back one day. It's impossible for a 10 billion solar mass giant to move freely in the Abell 2261 cluster's huge gravity field. If the speed of its recoil wasn't enough to set it free, gravity has been pulling it back the whole time. That's what the return situation is all about, a future where the runaway goes back home. In numerical simulations, a kicked black hole oscillates through its host's halo for hundreds of millions of years. Each swing carries it thousands of light years from the center before friction from dark matter, gas, and stars slows it down. With every pass, the oscillation shrinks, the orbit decays, and eventually the black hole settles again at the bottom of the gravitational well. Astronomers call this process dynamical friction capture, and for a galaxy as massive as Abell 2261, the timescale could easily be under 1 billion years. A blink in cosmic time. If that's happening right now, then somewhere in the cluster's haze, the missing black hole is arcing slowly back toward the galaxy that once held it. It wouldn't fall straight in. Its path would spiral, curving through the intracluster gas, compressing and heating it as it moves. That motion could generate faint X-ray ripples, tiny concentric waves of hotter plasma expanding outward. Chandra's next deep observations will look specifically for that pattern. The return would not be gentle. As the black hole plows back into the galaxy, it would drag its cloak of bound stars and dark matter along, The resulting shock could briefly reignite the core, compressing gas and triggering a burst of star formation around the impact zone. Some models predict a secondary quasar flare lasting a few million years, as the black hole reaccretes the gas it dislodged long ago. For the cluster, it would be like watching a dormant volcano erupt after an eon of calm. The gravitational consequences would be dramatic too. When the black hole finally settles, its enormous mass would recenter the galaxy's core, pulling the offset starlight back into alignment. The flattened brightness profile might steepen again, undoing the signature that first revealed the mystery. Future astronomers, billions of years from now, might look at Abell 2261 and see an ordinary elliptical, never suspecting that its heart once went missing. This cyclical pattern, merger, ejection, return, isn't unique to Abell 2261. Cosmological simulations suggest that many brightest cluster galaxies experience multiple black hole oscillations during their lifetimes. The process acts like cosmic breathing. Galaxies lose their cores in gravitational recoil events, then inhale their black holes back through slow gravitational drag. Each cycle redistributes stars and gas, regulating growth and feeding the cluster's long-term evolution. Abell 2261 might simply be caught mid-breath. If the return does happen, it might happen at the same time that new galaxies are being formed in the cluster. As smaller systems fall in and send gas through Abell 2261's ring, that gas could feed the black hole coming in, speeding up its trip home. If there is a new burst of accretion, the center could become bright again, turning this quiet corpse into the main light of the cluster. The galaxy's long quiet would finally end at that moment. The ghost would come home, and the universe would remember how loud it can get. That won't just end a secret when it happens. It will prove a point. Even the most wildly thrown objects can find their way back with the help of the forces that threw them away in the first place. There is still a chance that Abell 2261's story has a happy finish, but it will take hundreds of millions of years to play out. The future eyes of the universe. Abell 2261 is keeping it secret for now. That won't last forever, though. From now until 2050, many more telescopes will be built that will look at this galaxy. These telescopes will be better and longer than any others that have been made so far. If they work together, they might finally find out where the lost supermassive black hole is and whether it is hiding, wandering, or on its way home. At the top of that list is JWST, already scanning the universe in infrared with clarity beyond what even Hubble imagined. Its instruments can peer through dust and detect faint heat from cold stars, scattered gas, or a cloaked black hole. If Abell 2261's heart hides a dormant monster shrouded by debris, JWST's mid-infrared spectrographs should see the telltale warmth, a pinprick of light where every other wavelength sees nothing. And because JWST can study the chemical fingerprints of the stars near the center, it might spot gravitationally disturbed stellar populations, the fingerprints of an invisible mass. Next comes the Nancy Grace Roman Space Telescope, slated to launch later this decade. With a field of view hundreds of times larger than Hubble's, Roman will be able to sweep the entire Abell 2261 cluster for off-center sources, looking for the faint glow of a runaway nucleus. If the black hole escaped and now drifts somewhere nearby, Roman could catch it as a tiny, fast-moving smudge among the cluster's galaxies. Its wide survey mode will be essential for finding what smaller telescopes might overlook, the faint star cluster that's quietly following the black hole through the void. The Square Kilometre Array, SKA, will listen in radio frequencies for relic signals. It will be sensitive enough to detect the weakest synchrotron radiation from the old radio lobes around Abell 2261 and trace how those lobes have faded. By measuring how the magnetic fields twist and stretch across the cluster, astronomers could reconstruct the direction and strength of the original jets, effectively backtracking the black hole's last known trajectory. But gravity wave monitors in space will be the most important eyes of all. The Laser Interferometer Space Antenna, LISA, which will be launched in the 2030s, will be able to hear the hum of combining supermassive black holes all over the world. When Abell 2261's lost heart hits something again, it will leave a strong signal that LISA can pick up, whether it's in its own return or in a different galaxy. Even if the source is billions of light years away, the data could be tracked back to this cluster. This would link a merger happening now to a lost giant from a long time ago. And then there's Athena and Lynx, the next-generation X-ray observatories designed to map the cosmic web of hot gas with precision finer than a pixel of Chandra's. They'll be able to resolve the gas motions within Abell 2261's halo, searching for the tiny turbulence a drifting black hole would create. If they find a localized swirl of heated plasma, just a few thousand light-years wide, it could mark the wake of the missing core. When all of these tools work together, they make something like a network for cosmic detectives. Each person looks at a different part of the spectrum, which is like a puzzle piece. Some people look for heat, others for gravity, still others for motion, and still others for time itself. When all of their data comes together, scientists will be able to do something very cool. They will be able to watch how a galaxy changes after it loses its heart. They can see if galaxies can survive being sent into exile for good, or if the universe always finds a way to make things right. Echoes across the cluster. Even though there isn't a black hole in Abell 2261, it is not at all quiet. The galaxy's missing heart has left behind waves or echoes that still move through the cluster around it and shape it. It is made up of a sea of hot plasma called the intracluster medium. The intracluster medium is a faint X-ray glow that moves between the hundreds of galaxies that are held together by gravity. And in Abell 2261, that sea still has marks from what happened when the black hole in the middle of it disappeared. Astronomers using the Chandra X-ray Observatory noticed subtle asymmetries in the cluster's gas. Instead of a perfect sphere of heat, there were ripples, faint arcs and voids suggesting something once stirred the medium with enormous force. One theory holds that when the black hole was ejected, it didn't slip away quietly. It kicked through this hot plasma like a ship cutting through water, leaving behind waves of compressed gas that have yet to fade. Those waves stretch for tens of thousands of light years, frozen snapshots of the black hole's exit path. If true, these ghostly trails might eventually lead us to the culprit itself. A high-velocity black hole moving through intracluster gas would produce a bow shock, heating the gas directly in front of it and cooling the wake behind. Detecting that temperature gradient could finally confirm the black hole's trajectory. Unfortunately, those variations are so faint that even Chandra can barely see them, requiring exposure times of hundreds of hours to tease out. But future missions like Athena might do it in days, mapping the faintest whispers of motion through a billion-degree medium. Even harsher are the gravity echoes. The outflow from a supermassive black hole doesn't just move gas around, it also pulls on the galaxies around it, changing their paths slowly over time. A ripple in the gravitational field that can last for billions of years is caused when such a large object is ejected from a cluster core, according to computer models. In Abell 2261, the slightly off-balance arrangement of close galaxies may still be reacting to that event from a long time ago. Even if the core doesn't remember, the cluster does. Some scientists think those echoes could also explain a mystery of timing. The intracluster medium in Abell 2261 seems unusually cool compared to other clusters of similar size. Typically, a central black hole pumps energy into the gas through jets and radiation, preventing it from collapsing inward. Without that constant heating, the gas in Abell 2261 has cooled and condensed, forming faint filaments visible in ultraviolet light. Those structures are the fingerprints of a cool core cluster, one whose central furnace went out long ago. The missing black hole explains it perfectly. The cosmic heater turned off, and the cluster began to relax. But the echoes could also be a sign of what's to come. Cooled gas doesn't stay still forever. It falls inward, starting new star formation and sometimes waking up black holes that have been asleep. Those cooling strands could soon become the fuel for any part of the original center that is still there, like a smaller secondary black hole or the core that was pushed away. A weak flash of X-rays or a flickering of radio waves could be the first sign of life. The calm in the cluster could just be a break between two storms. The thought that the absence of a single black hole can affect a whole group of galaxies over hundreds of millions of light years is amazing. But gravity does that. It ties everything together. There is a web of matter that moves when one mass moves. Also, Abell 2261 still sounds like a bell that was rung a long time ago. Its gas, galaxies, and dark matter ring are all vibrating with the effects of an event that we're still trying to figure out. The hunt for the runaway. If the black hole really got away from Abell 2261, it didn't just disappear, it became a runaway, floating through space like a ghost ship with its crew still on board. That idea isn't just a thought experiment either. Astronomers have already started looking for it. They are looking at the cluster around it for signs of a small, fast-moving light source that could show them where the runaway is. The most promising leads come from Hubble and Subaru data, which revealed several off-center star clusters near Abell 2261's core. Each one looks like a faint, blurry knot of starlight. Small, dim, but oddly massive for its brightness. One in particular, located about 2,000 light-years from the center, shows unusual motion and color. It could be exactly what scientists expect, a hypercompact stellar system, a miniature galaxy clinging to a runaway black hole's gravity. When a supermassive black hole is ejected, it often drags its closest stars with it, creating a tiny bound cluster that travels as a single unit through space. Detecting one is like spotting a grain of dust against a spotlight. These systems are small, only a few dozen light-years wide, and faint, visible only with the sharpest imaging and clever filtering. But their spectra give them away. The stars within move at incredible speeds, up to 1,000 kilometers per second, far faster than any ordinary cluster. That velocity broadens their spectral lines, leaving a distinct signature that screams, "Something massive is hiding here." So far, none of the candidate clusters have shown that velocity spread clearly enough to confirm the runaway, but the limits are tightening. The next generation of instruments like JWST's NEOSPEC and the 30-meter telescope will have the precision to measure even subtle motions within these faint glows. If one shows evidence of stars whipping around an unseen point, it would be the first direct detection of a supermassive black hole exiled from its home galaxy, a discovery so profound it would rewrite the understanding of galactic evolution. And there's another clue that's even more subtle. A runaway black hole moving through the thin intergalactic medium should leave a trail of ionized gas, glowing faintly in ultraviolet. It's the cosmic equivalent of a contrail behind a jet, produced as the black hole's gravitational field compresses and heats the surrounding plasma. This faint streak could stretch for thousands of light-years, but it would be visible only through deep imaging in very specific wavelengths. Detecting it would require patience, and probably the combined effort of multiple telescopes working in sync. The idea of a supermassive black hole wandering alone sounds lonely, but it might be surprisingly common. Some simulations suggest that up to 10% of all supermassive black holes have been ejected at some point in cosmic history, flung out during violent mergers. Most eventually settle into new galaxies or fall back into their old ones, but a few keep going, traveling through the void for eternity. Each one is an invisible traveler, surrounded by a small halo of loyal stars, carrying the memory of its lost galaxy. If the Abell 2261 runaway is real, it might be the closest chance yet to study one. It could reveal how galaxies recycle their cores, how gravity and momentum play tug-of-war on unimaginable scales, and how the universe disperses its heaviest objects. Some astronomers even speculate that such wanderers could explain faint, unexplained X-ray flashes seen in deep sky surveys, brief moments when an intergalactic black hole devours an unlucky star. And what is the most exciting possibility? We might see it move one day. A very small change, a few thousandths of an arcsecond, could show how it moves through space if its location is tracked over many years. It will be a big deal in astronomy when the first runaway supermassive black hole is seen traveling. We will not only understand how galaxies die, but we will also be able to see their ghosts move free. The hidden cluster within. Even though Abell 2261 doesn't have a black hole, there is another mystery that is right in front of our eyes: the cluster within the cluster. Deep optical and infrared images have shown that Abell 2261 is not just one galaxy with many smaller ones around it. It's like a tiny environment, with a swarm of smaller galaxies, filaments, and faint tidal remains moving around inside its halo. Some scientists think that these pieces might help them figure out where the black hole went. When massive galaxies collide and merge, they don't dissolve cleanly. Their stars scatter, but many remain locked together in dense knots called satellite cores, leftover nuclei that orbit the central galaxy like moons. In Abell 2261, at least 4 such cores have been identified near the main center. Each has a different shape, brightness, and velocity, suggesting they're the fossil remains of galaxies that once fell into the cluster's heart. One of them, about 10,000 light-years from the center, is unusually compact and red, possibly the nucleus of the last galaxy to merge with Abell 2261 before the black hole vanished. That connection is more than coincidence. The missing black hole event likely happened right after that final merger. If so, one of these subcores could still be carrying a gravitational imprint, either a leftover black hole of its own or the stellar trail of a much larger one that escaped. By mapping the motions of these inner galaxies, scientists hope to triangulate the recoil direction of the original supermassive black hole. It's like reconstructing a cosmic crime scene, with each stellar remnant serving as a witness frozen in orbit. The internal structure of Abell 2261 is bizarrely puffy. Instead of a concentrated bulge, its core is an extended, low-density region roughly 10,000 light-years wide. This kind of diffuse center is typical in galaxies that have undergone violent scouring, a process where binary black holes, before merging, sling nearby stars outward through gravitational slingshot effects. In the final moments before a merger, 2 massive black holes can literally excavate their surroundings, leaving behind a hollowed-out core. That might be exactly what we're seeing in Abell 2261, the carved-out cavity left after its central duo merged and then recoiled out of view. Within that cavity lie faint glows, clouds of red stars, barely visible even in long exposures. Some of these could be remnants of the accretion disk, or the shredded remains of star clusters once orbiting close to the central pair. Others might be newly formed stars, ignited by the shock waves of the ejection event. The mix of old and young light gives the region a strange duality, ancient yet disturbed, still trembling from something colossal that happened long ago. From farther away, the galaxy's ring shows weak shells and streaks, which are made up of stars that have been pushed around by tides. These features, which look like fingerprints of past crashes, show scientists how many times the galaxy has been merged. When there are more shells, the past is bad. Abell 2261 has a lot. Every one of them points to another galaxy being wiped out, another step toward the supermassive collision that probably sent the galaxy's center black hole into space. Smaller black holes could also live in the inner subclusters. Some of them might have black holes with middling masses that are left over from when they were galaxy centers. If the giant black hole that went off on its own hasn't come back, one of these smaller ones might now be in charge of the gravity field, acting as a temporary heart. To find them, we will need high-resolution X-ray and radio data, but their fingerprints might help explain the faint leftover energy that is still being found in the area. When black holes collide. All the clues in Abell 2261's ghostly core point to the same event: 2 black holes so big colliding that they shook the galaxy to its core. 2 very large galaxies moved together in the Abell 2261 cluster billions of years ago, pulled together by their own gravity. Every single one had its own enormous black hole in the middle, And as the galaxies joined together, those huge, unseen black holes did too. Their dance was slow, violent, and life-changing. It was the kind of meeting that leaves the universe's darkest scars. When the galaxies first met, their stars mingled like currents in a storm, forming tidal tails and loops. The central black holes, meanwhile, spiraled toward each other through a process called dynamical friction, their immense gravity dragging through the surrounding stars and gas, stealing momentum until the pair finally settled into a tight binary at the galaxy's center. For millions of years, they circled one another, each orbit shrinking as they hurled nearby stars outward in three-body slingshots. That ejection of mass hollowed out the galaxy's heart, explaining why Abell 2261's center looks so unusually flat and diffuse today. Eventually, only gas and space-time itself remained to slow them down. As the two black holes drew within light days of each other, their motion began warping the very fabric of the universe. Gravitational waves, ripples in space-time predicted by Einstein, radiated away energy, tightening their orbit until, at last, they merged in a burst of unimaginable power. For a brief moment, the system outshone all the stars in the galaxy combined, not in light, but in gravity. Then came the recoil. Because gravitational waves aren't emitted perfectly symmetrically, their final burst imparted a kick to the newly merged black hole. Depending on the masses and spins involved, that recoil can reach several thousand kilometers per second. If the new black hole was kicked hard enough, it could have been launched clean out of the galaxy, the exact scenario that best fits Abell 2261's current emptiness. That kind of event wouldn't just disturb a galaxy, it would redefine it. The ejection would scatter the innermost stars, redistribute angular momentum, and create the hollowed plateau astronomers see today. It might even have altered the orbits of entire satellite galaxies, spreading subtle asymmetries across the cluster. If the kick velocity was lower, the black hole might have stayed gravitationally bound, but oscillated through the galaxy for eons, damping down only after billions of years. Either way, the system would carry the memory of that cosmic punch. The smoking gun would be a gravitational wave echo, faint ripples in space-time left over from the merger. We can't detect such ancient waves directly yet, but upcoming missions like LISA might one day listen for them. Even now, astronomers can look for indirect evidence: the pattern of stellar motions, the density drop at the core, and the asymmetric distribution of hot gas, all consistent with a massive recoil event. Researchers are also excited about the idea that we might be seeing a galaxy that has recently merged and is in the middle of recovering. On this size, black holes don't collide very often, but they're what build the universe's biggest structures. Every time two galaxies unite, their center black holes join together. The mass of these two black holes creates the next generation of cosmic giants. Abell 2261 might be the missing evolutionary link, the after picture in a series that shows how regular galaxies turn into the huge center hubs of clusters. If this is true, Abell 2261 would also show us what the future holds for our own Milky Way. When our galaxy and Andromeda combine in about 4 billion years, their black holes, which are each millions of times the mass of the Sun, will make their own binary. The process we see frozen in Abell 2261 could happen in our sky one day, changing the way our children and grandchildren will sleep. The silent aftermath. Abell 2261 went into a long, strange silence after the violent merger that probably threw out its heart. This is the quiet phase of a galaxy that has lost its power source. In a normal galaxy, the core is very busy. Gas falls in and heats up to millions of degrees, giving off X-rays while jets and winds blast outward, changing the history of the galaxy. In Abell 2261, though, all of that force was gone in an instant. There is now a strange calm that comes from a cosmic disaster that happened hundreds of millions of years ago. There are signs of that silence all over the place. An X-ray picture from Chandra shows a smooth, dim glow with no bright spot in the middle. A radio jet, an accretion disk, and an ionized gas thread do not connect the core to its surroundings. The heart of the galaxy is as still as water in the deep. Even the distribution of starlight, which is usually sharp in the center, flattens out into a soft slope. Astronomers don't see that flatness as beautiful. They see it as proof of loss. This means that the stars that used to revolve around the black hole are now spread out, with longer paths between them, because of the recoil event. The smoothness of the core is a scar, and its unity isn't what it seems to be. The quiet, though, might not be eternal. Galaxies are rarely static, and Abell 2261 still sits in a cluster brimming with gas, dust, and smaller galaxies. Over cosmic time, that material will drift inward. Even without a central black hole, gravity will gradually gather it. As it settles, friction and compression will reignite star formation, slowly rebuilding a luminous core. If the ejected black hole eventually returns, or if a smaller one merges from an infalling satellite, the galaxy's nucleus could flare back to life in a new quasar phase. Right now, the system is a cosmic tomb, but one filled with dormant potential. The gas surrounding it still emits faint X-rays, meaning it's hot enough to feed a future nucleus if one reappears. The stars in the outer regions continue their slow dance, holding the structure together. In deep optical images, astronomers can even see subtle ripples, ghost-like shells of light tracing the last gravitational convulsions from when the black hole left. The scene is calm but not frozen. Every particle of gas, every drifting star, is part of a long reset. The silence also holds scientific power. For astrophysicists, Abell 2261 provides the perfect laboratory for testing feedback theories, models that explain how black holes regulate galaxy growth. Without an active nucleus, the galaxy's gas has cooled unchecked, forming structures that can be compared directly with simulations. By studying how the system evolves without a central engine, astronomers can finally measure how much influence black holes really exert on their hosts. In other words, this galaxy's silence lets us hear how loud gravity truly is when the loudest voice is gone. In that quiet, there's also a small secret hidden in the lack of dust. Usually, these kinds of galaxies have lines of cold dust near their cores. This dust is left over from when stars were being formed. But that dust doesn't seem to be there in Abell 2261. One idea is that when the black hole ejected, it sent out a blast that was strong enough to wipe it out, leaving behind only faint stars. Another idea is that the radiation from the quasar phase before the explosion just vaporized everything. In either case, there is only a core left to hide. The galaxy then drifts, huge, bright, and weirdly empty. In our time, Abell 2261 would be an old city that had lost its fuel source. The buildings and lights are still there, but there is no longer any pulse. The stars keep going around like they always do, not realizing that their support has been taken away. Every photon coming from its pale core is a message of resilience, proof that the universe keeps going even after it falls apart. Lessons from a missing heart. It's not just a wonder that Abell 2261 is, it's a lesson written in the stars. Astronomers thought for a long time that the core of every big galaxy must contain a giant black hole. That rule was so reliable that it shaped whole models of how the universe evolved. One thing, though, this empty space where a black hole should be has made scientists question what they thought they knew. What if galaxies can live without the gravity that holds them together? What if black holes' lives aren't tied to the galaxies that made them? The first lesson is about resilience. Despite losing its nucleus, Abell 2261 remains gravitationally stable. Its stars haven't flown apart, its structure hasn't unraveled. It suggests that galaxies may be more self-sustaining than previously thought, able to maintain shape through the combined gravity of stars, dark matter, and lingering gas. The missing black hole changed its center, not its soul. That stability challenges the traditional view that black holes are absolutely essential for galactic cohesion. Perhaps they're catalysts for growth, but not lifelong caretakers. The second lesson is about timing. Abell 2261 shows us that galaxy mergers don't always end neatly. The supermassive black hole merger that caused this mystery happened billions of years ago, yet its effects are still visible now. Proof that cosmic events leave traces that last far longer than the events themselves. The void in its core, the flattened star distribution, and the absence of radiation are time capsules. They remind us that the light we see today is a snapshot of a slow recovery still unfolding. The universe changes, but never all at once. The third lesson is about connection. The fate of this galaxy reveals that no cosmic event exists in isolation. When its black hole was ejected, the shockwaves rippled across the cluster, altering the temperatures, densities, and motions of surrounding galaxies. One object's disappearance became an entire environment's transformation. It's a vivid reminder that the universe is a single entangled system, gravity binding every structure to every other, even across millions of light years. Abell 2261 also teaches people to be humble. Even with all of our technology, we're still putting together bits and pieces of old events from the tiniest flickers of light. Even the heaviest things in the universe can disappear, leaving only faint patterns for us to figure out. Astronomy is like a big-time detective story, and Abell 2261 is one of the hardest blanks in that story. Every picture taken by Hubble, every X-ray pattern from Chandra, and every computer exercise are all attempts to piece together something we'll never see for ourselves. And yet, through those efforts, we learn not just about black holes, but about how knowledge grows. A single anomaly can reshape entire fields. The missing heart of Abell 2261 has already pushed theorists to refine models of galaxy mergers, gravitational recoil, and cluster dynamics. It's even helped prepare scientists for future discoveries. When LISA and other observatories begin detecting gravitational waves from merging supermassive black holes, this galaxy will serve as the prototype for what happens next. It's also an alert. If an event this huge can erase all clear signs of a black hole, how many others have already happened without being seen? How many galaxies that look like they ought to be normal are actually quiet survivors of the same process? We might not be able to see ghosts in the universe yet. There may be galaxies whose hearts were thrown into the dark long before we ever looked their way. The mystery that redefined the cosmos. Abell 2261 started out as a tiny dot in the constellation Hercules. It was just another group of galaxies that was far away and being studied by telescopes on Earth. But the fact that it didn't break any cosmic rules made it one of the biggest puzzles in astronomy this century. It went against the norm. It called into question the idea that black holes stay in the middle of galaxies forever. Scientists now have a new way to think about how the world grows, breaks, and builds itself back up again. Before this discovery, astronomers treated the bond between galaxies and their black holes as sacred. The bigger the galaxy, the bigger its central black hole, a rule confirmed across hundreds of systems. But Abell 2261 shattered that simplicity. Here was a giant galaxy, 10 times the Milky Way's mass, with no detectable core engine. The finding forced researchers to ask uncomfortable questions. Could black holes wander freely across space? Could galaxies live in the aftermath of gravitational recoil? Could entire clusters carry hidden travelers, supermassive bodies drifting invisibly between galaxies? Those questions have rippled far beyond this one case. Abell 2261 has become the cornerstone of new recoil physics, shaping how simulations handle the aftermath of black hole mergers. It also guided the design of instruments meant to find the wanderers themselves. NASA's upcoming missions, LISA for gravitational waves, Roman for wide-field surveys, and LYNX for ultra-deep X-ray imaging, are all in part built to find what Abell 2261 implies must exist. And scientists find more echoes the more they look. Some galaxies like 3C186 and SDSS J0927 plus 2943 now have cores that are out of place, or black holes that are running away. Each finding is linked to the same understanding that Abell 2261 sparked. Black holes are not fixed landmarks, but rather moving results of how the universe is changing. In their surroundings, they move, join, recoil, and change its form. The universe isn't neat, it's alive, changing, and always putting itself back together after its own fits and starts. What makes Abell 2261 so powerful as a story is how much of it depends on absence. No explosion, no visible jets, no grand finale, just a missing shadow in a sea of light. And yet, from that void, humanity has built entire theories. In a way, this galaxy became a mirror for our curiosity. It showed how much we can learn from what we cannot see. JWST's latest surveys have returned to Abell 2261, stacking deeper exposures to hunt for faint heat signatures that might mark the runaway's trail. So far, there's still no detection, just the same haunting calm. But every null result tightens the puzzle, narrowing the possibilities, forcing the next hypothesis to be sharper, smarter, and bolder. The investigation itself has become a symbol of science's persistence, a chase across billions of years of light following the faintest traces of gravity's footprints. We'll get an answer one day. It could be from a future gravitational wave that Lisa caught in the middle of its scream and tracked back to a faraway cluster. It could be a tiny glow seen by a telescope that hasn't been built yet. Or it could be that they realize the truth is stranger than any theory they have now, that the black hole didn't go away at all, but changed shape in ways we can't even imagine. No matter what happens, Abell 2261 will always be remembered as the star that changed the rules of astronomy. Weighing a star near the limit. It seems strange to think about weighing a star that is only 20 kilometers wide but has more mass than the Sun. That task isn't just a test of measuring skills for the Black Widow pulsar, it's a matter of life and death. Because we can tell if it's still a neutron star or already close to becoming a black hole by finding out how much mass it has. Scientists are getting a better look at it. This is one of the biggest neutron stars ever found. It is so close to the theoretical limit that it seems defiant to still be there. When astronomers first tried to pin down the mass of the Black Widow, they used one of nature's simplest tools, orbital motion. Even though the companion star in the system is small and faint, it still tugs on the neutron star just enough to make it wobble. By measuring the precise timing of the pulses, scientists can track that wobble and calculate how massive both objects must be. The result was startling. The pulsar weighed about 2.35 times the mass of the Sun, a record breaker that instantly made headlines. To get an idea of how big that number is, picture fitting 2.5 suns into a shape that is just a bit bigger than Manhattan. It has a density of more than 1 billion tons per teaspoon, and the pressure inside is higher than the pressure in the center of an atom. At those levels, it gets harder to tell the difference between regular matter and something else. There are so many neutrons inside that they might break apart into a soup of quarks, which are the building blocks of all particles. If proven, the Black Widow could be the first known example of a hybrid star, which is somewhere between a neutron star and a quark star. It is half solid and half fluid, and its physics are so complicated that no lab can duplicate them. But what really has NASA's attention is how close this mass is to the Tolman-Oppenheimer-Volkoff limit, the upper boundary where even quantum forces can no longer resist gravity. For decades, physicists have debated exactly where that line lies. Some models put it around 2.2 solar masses, others 2.5. The Black Widow sits right in the middle, a living test of which theory is right. If it remains stable, the limit must be higher than we thought. If it collapses, the limit just found its proof. Either way, it will redefine how we understand the structure of matter itself. To measure such tiny variations, astronomers rely on a technique called pulse timing analysis. Every pulse from the neutron star arrives at Earth with microsecond precision. When the star moves slightly in its orbit, the pulses reach us sooner or later depending on its position. like listening to a metronome while walking toward or away from it. By tracking those shifts over months or years, researchers can calculate the system's orbital parameters with astonishing accuracy. The margin of error is less than 1 part in a billion. And that's what allows us to weigh an object we can't see. The facts make it clear. The partner star is very light. It has only 0.02 solar masses, which is about the same as Jupiter. The pulsar, on the other hand, controls the whole system. It pulls the partner into a long circle and removes its matter. As that stuff falls in, it gives the neutron star tiny amounts of mass. The rate is slow, but it keeps going. It adds about 100 million tons of matter every second, which is a very small part of its overall mass, but over millions of years, it's enough to make a change. The risk grows over time. With each new layer of material that falls into the star, the inside gets even more compressed. Eventually, there will be no known force that can stop gravity from squeezing the star apart. Measuring that growth in real time is almost impossible, but subtle clues appear in the pulse pattern. As the star gains mass, its moment of inertia changes slightly, altering its spin-down rate. NASA's NICA and Fermi observatories watch those changes constantly, comparing data across years to see if the rhythm of the pulses drifts. Even a microsecond deviation could suggest a shift in internal structure, a hint that the star is getting heavier or denser. So far, it's holding steady. But steady doesn't mean safe. The real question is whether the Black Widow has already passed the tipping point. The collapse from neutron star to black hole happens in microseconds, and there's no external signal to warn us. If it happened 14,000 years ago, the time it takes for its light to reach us, we wouldn't know yet. All the data we gather are echoes from the past. That's the eerie part of studying objects this far away. We're never watching the present, only the delayed replay of ancient events. Astronomers are still measuring, timing, and making models. Each new discovery narrows the puzzle and makes the number more accurate. If the end result proves that the Black Widow really does weigh at least 2.35 solar masses, we will be looking at the very edge of physics. We will be looking at a star that is sitting on the edge of what is possible, showing us how close matter can get to falling apart infinitely without crossing that line. The Tolman-Oppenheimer-Volkoff ceiling. There is a point at which all kinds of matter break. When force goes over tensile strength, steel breaks. For white stars, it's when gravity is stronger than the pressure of the electrons. The Tolman-Oppenheimer-Volkoff limit, or TOV limit, is one of the most important but little-known ideas in astronomy. It tells us what the point of no return is for neutron stars, which are the densest things, not quite a black hole. The unseen roof is what separates what can stay and what has to fall. Being just below that line, the Black Widow pulsar is a live stress test of nature's strictest limit. The concept dates back to 1939, when 3 physicists, Richard Tolman, J. Robert Oppenheimer, and George Volkoff, asked a radical question. How much matter can you squeeze into a sphere before it implodes under its own gravity? They knew that electrons could only resist compression up to a certain point, the Chandra limit, about 1.4 solar masses. Beyond that, even electrons would be crushed, forming neutrons and creating a neutron star. But what happens when even neutrons can no longer resist? Tolman and his colleagues worked through Einstein's equations of general relativity and found that there's a limit there too, roughly 2 to 3 times the mass of the Sun. Beyond that, gravity can't be stopped. No matter how hard the neutrons push back, the inward pull wins, and the object collapses into a black hole. Inside a neutron star, matter isn't arranged in neat layers or atoms. It's a continuous fluid of neutrons compressed so tightly that quantum mechanics becomes the only thing holding it up. Each neutron occupies its own quantum state, generating a collective pressure known as degeneracy pressure. That pressure is astonishingly strong, but it has a limit. As the star gains mass, its own gravity increases faster than that degeneracy force. Once the density passes the TOV threshold, space-time curves so sharply that even the pressure of degenerate neutrons can't push back. the equations collapse right along with the star. Because it is not a fixed number, the TOV limit is both compelling and unnerving. It rests on the strange physics of ultra-dense matter, which we have never seen for ourselves. It is still not clear what the exact equation of state is that controls neutron matter. Different models say the ceiling could be as low as 2.1 solar masses, while others say it could be as high as 3.0. That's why each measurement of a big neutron star is important. It changes the edge. Because the Black Widow pulsar was 2.35 times the mass of the Sun, it forced scientists to raise the roof. That meant the stuff inside had to be even stronger than we thought. It had to be able to handle more pressure before giving up. But there's another side to this. If a single observation were to show a neutron star heavier than the TOV limit, it wouldn't just rewrite textbooks. It would shake the foundations of general relativity. That's because the TOV limit isn't just about matter, it's about space-time stability itself. Once the core becomes too compact, no known force can halt the collapse. The density increases until an event horizon forms, and space-time pinches off from the rest of the universe. The moment that happens, the object stops being a neutron star altogether. It becomes a black hole. In practice, we've never caught that transition happening. It's too fast, too quiet, and too far away. But the Black Widow pulsar could give us the closest look yet. If its mass measurement nudges even slightly upward, we'll know it's approaching the cliff. NASA's NICA mission is designed precisely for that kind of test. By analyzing X-ray light curves as the star rotates, it can infer how gravity warps the light leaving its surface. The stronger the warping, the greater the mass. Those data, combined with radio timing, let scientists determine whether the Black Widow is climbing toward or holding steady beneath the limit. A further intriguing fact is that rotation changes everything. Because centrifugal force fights gravity, a neutron star that spins quickly can hold a little more mass than one that stays still. The Black Widow might already be farther away than the TOV limit for a star that isn't spinning, since it's only stable because it's spinning so fast. So long as it doesn't slow down even a little, that support will go away. The star might fall apart almost right away, skipping the whole supernova stage. From our point of view, its heartbeats would just stop. That's one reason NASA keeps a close eye on its rotation. A sudden slowdown could be the first time scientists see a neutron star cross the TOV line in real time. And that's the story of Abell 2261, the galaxy that lost its heart and changed everything we thought we knew about black holes. Somewhere out there, its runaway core may still be drifting through the dark, waiting to be discovered. If you enjoyed this deep dive into one of the universe's greatest mysteries, don't forget to like, subscribe, and turn on notifications so you never miss a journey like this again. Now tap the next video on your screen. We'll see you there.